Hello and welcome to this revision session for AQA A-Level Physics, Paper 2, looking at the topic of nuclear physics, in particular nuclear decay. So if we're being successful and we've learnt in today's revision session, what we should be able to do is firstly answer A-Level Physics examination style questions, assess our understanding on A-Level Physics, then understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? When you're completing your revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your work and answers to the questions in the revision session. When you're doing this, make sure you write in full sentences and show your full working out. So now in the right hand side, in this section, write down any bits of information which you find useful, any hints and tips from answering the questions in this revision session. So at the end of this revision session, you should then write up your notes into a revision sheet for you to use independently. So how should you be revising for AQA A-Level Physics? Well, the first step is to learn the key facts. Use revision guides, class workbooks, student prep notes and the textbooks to learn the key ideas of the course. Now you may wish to make mind maps or to write out notes yourself. Secondly, test yourself. Use things like Caboodle, Seneca, the knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. Finally, you want to practice exam style questions. So use exam prep books, homework books, supervised study books and additional workbooks to answer exam questions and to mark your own work. Now you may wish to download your own exam past papers to do this. So how can we revise our physics? So the first step is to learn the key facts, then it's to test yourself, and then it's to practice exam style questions. So what are the key facts for nuclear physics? Well, firstly, we've got Rutherford scattering. Alpha particles are directed at a thin gold foil. Most pass through and some were deflected at large angles. This led to the conclusion that the atom is mostly empty space. The positive charge of most of the mass are concentrated in a small dense nucleus. Now the historical development was it replaced the plum pudding model and marked a significant shift in the understanding of atomic structure. For alpha, beta and gamma, we know alpha is the helium nucleus, it's stopped by paper and is highly ionizing. Beta are electrons, stopped by aluminium and are moderately ionizing. Gamma is EM waves stopped by thick lead and are weakly ionizing. Now they're identified using absorption experiments. They have many applications such as medical uses and in industrial uses such as the thickness monitoring and foil production. Now the key equation is the inverse square law for gamma radiation. I is equal to a constant over x squared. Now radioactive decay is a random spontaneous process. Each nucleus has a constant probability of decay. Our key equations are the rate of decay, which is the change in n over the change in t is equal to minus lambda n, where lambda is the decay constant in seconds to the minus 1. Our number of nuclei remaining is n is equal to n0 e to the power minus lambda t. Our activity is A equals lambda n or A equals A0 e to the power minus lambda t. In half-life is going to be equal to log 2 over the decay constant. Now for nuclear instability, the graph of n, the neutrons, against z, the proton, shows the stability line for nuclei. Stable nuclei lie close to the line. We must be aware of the decay modes of unstable nuclei, alpha, beta minus, beta plus and electron captures, and know the decays what they cause changes in n and z. So for example, beta minus increases z by 1 and decreases n by 1. We know that in excited states, nuclei may emit gamma rays as they return to the ground state, and technetium-99m in medical diagnosis is used as a gamma-emitting radioactive tracer. So let's have a look at some general questions to do with nuclear physics. What observation from Rutherford's gold foil experiment led to the nuclear model of the atom? The observation that small numbers of alpha particles were deflected at large angles suggested the presence of a dense positively charged nucleus. What conclusion about the atom was drawn from most alpha particles passing straight through the foil? That atoms are mostly empty space. How did Rutherford scattering change our understanding of atomic structure? It replaced the plum pudding model with a nuclear model where mass and positive charge are concentrated in a tiny nucleus. Which type of radiation is most strongly ionizing and least penetrating? Alpha radiation is the most ionizing but also the least penetrating. Which type of radiation is the most penetrating but least ionizing? Gamma radiation. The following question says, what is the basic principle of using beta radiation to monitor the thickness of aluminium foil? The amount of beta radiation that passes through the foil and reaches the detector varies with the thickness of the foil. This allows adjustments to be made. What observation from Rutherford's gold foil scattering experiment led to the nuclear model of the atom? The observation that a small number of alpha particles were deflected at large angles suggested the presence of a dense, positively charged nucleus. What observation from Rutherford's gold foil experiment led to the nuclear model of the atom? The observation that a small number of alpha particles were deflected at large angles suggests the presence of a dense positively charged nucleus. Why can gamma radiation follow an inverse square law? Because it spreads out uniformly in all directions from a point source. Give 2 examples of background radiation and explain how one can be accounted for in experiments. Examples include cosmic rays and radon gas. Background radiation can be accounted for by measuring it separately and subtracting it from experimental results. Why is the safe handling of radioactive sources important? It is to minimize exposure and reduce the risk of biological damage from ionizing radiation. What does a graph of neutron number n against proton number show for stable nuclei? It shows a stability line where stable nuclei lie. As Z increases, n becomes greater than Z for stability. What type of decay typically occurs when a nucleus has too many protons? You would either get beta plus decay or electron capture. What type of decay typically occurs when a nucleus has too many neutrons? Beta minus decay. What happens to the proton and neutron numbers during alpha decay? The proton number would decrease by 2 and the neutron number decreases by 2, so the mass number decreases by 4. In beta minus decay, what are the changes in n and z? A neutron is converted into a proton, so z increases by 1 and n decreases by 1. How does electron capture change the composition of a nucleus? A proton captures an inner orbital electron and becomes a neutron, decreasing Z by 1 and increasing N by 1. Why does gamma radiation often follow alpha or beta decay? Well, because the daughter nucleus is left in an excited state and emits gamma rays to return to a lower energy state. What is the role of technetium-99m in medical diagnosis? It is used as a gamma ray source in medical imaging due to its short half-life and emission of penetrating detectable radiation. What is a nuclear energy level diagram used for? It's there to represent the different energy states of a nucleus and transitions involving gamma emissions. What does the M stand for in technetium-99m? It indicates that the nucleus is in a metastable or excited state. What is meant by the random nature of radioactive decay? It means that we cannot predict exactly when a specific nucleus will decay, only the probability it will over time. What does the decay constant lambda represent? The probability per unit time that a nucleus will decay. Define activity in the context of radioactive decay. Activity is the number of decays per unit time measured in becquerels. How can half-life be determined from a decay curve? By measuring the time taken for the activity or number of nuclei to halve from any starting value. What experimental technique uses the deflection of alpha particles to estimate nuclear radius? It is the distance of closest approach of alpha particles Rutherford scattering. What assumption is made when alpha particles have the using the closest approach to estimate the nuclear radius? It is that all kinetic energy is converted into electrostatic potential energy at the point of closest approach. What type of wave behaviour is used to determine the nuclear radius using high energy electrons? It is electron diffraction. What does the equation R equals R0 a to the power a third suggest about nuclear material? It indicates to us that nuclear material has a constant density. Why does nuclear density remain constant across different nuclei? This is because both mass and volume increase proportionally with nucleon number. What is significant about the first diffraction minimum in the electron diffraction graph? It provides the data needed to calculate the nuclear radius based on the wave interference patterns. Let's now have a look at some questions to do with nuclear physics. Technetium-99m is a metastable radioactive isotope used in medical imaging. It decays to a more stable state by emitting a gamma photon. The isotope is produced from the decay of molybdenum-99. A simplified energy level diagram for the decay is shown below. Describe the changes to the nucleus that occur when molybdenum-99 decays to technetium-99 by beta minus decay, and when technetium-99m decays to technetium-99 by gamma emission. In each case, state how the values of Z and N are affected. Explain how the position of a nucleus on an NZ graph can indicate whether it's likely to decay by beta minus decay, beta plus decay, or electron capture. Discuss why technetium-99m is a suitable isotope for medical diagnostic imaging. Your answer should include reference to the type of radiation emitted, half-life, penetration energy, and safety considerations. So pause the video now, and then unpause the video when you want to go through your answer. Right, in this question, in beta minus decay, a neutron converts to a proton, so Z increases by 1 and N decreases by 1. In gamma decay, the nucleus moves from an excited to lower energy state, so there's no change to Z or N. Now, the stable nuclei lie along a curved band, the line of stability on an NZ graph. The nuclei above the line have too many neutrons and are likely to decay by beta minus. Nuclei below the line have too few neutrons and likely to decay by beta plus or electron capture. The decay returns the nucleus close to the line of stability by adjusting the neutron-proton ratio. Now, we would use technetium-99m as it emits gamma radiation, so penetrates tissues and can be detected externally. It has a short half-life of about 6 hours, long enough for imaging but short enough to minimize dose. The gamma radiation causes less ionization and no change to chemical identity, making it safer for the patient. An excited nucleus of cobalt-60 undergoes 2 gamma emissions to reach its ground state. The table below shows the 3 nuclear energy states of cobalt-60. Calculate the energy in MeV and joules of each gamma photon emitted during the transition from state A to state B and state B to ground state. Determine the wavelength of the gamma photon emitted during the A to B transition. Then explain why gamma radiation is more suitable than alpha or beta radiation for diagnostic imaging. So pause the video now, and then unpause the video when you want to go through your answer. Right, in our first question, we know A to B has an energy of 1.17 MeV, whilst from B to ground it's 1.33 MeV. We can then convert both the answers by multiplying 1.6 times 10 to the minus 13 to get into MeV. So it becomes 1.87 times 10 to the minus 13 joules and 2.13 times 10 to the minus 13 joules. We know that the energy for the A to B transition is 1.87 times 10 to the minus 13 joules. We know that lambda equals hc over E. We pop in all our values and we get 1.06 times 10 to the minus 12 meters. Now, gamma rays are highly penetrating and can pass through the body. Detectors outside the body can register gamma emissions. Now, also, gamma rays cause less ionization compared to alpha or beta, making them safer for diagnosis. And alpha and beta particles are absorbed quickly in tissues and would not escape the body for detection. An alpha particle with kinetic energy 5.5 MeV is fired towards a gold nucleus, atomic number 79. At its point of closest approach, the alpha particle momentarily comes to rest. The molar mass of gold is 197 grams per mole. Using energy conservation, estimate the closest approach distance between the alpha particle and the gold nucleus. Assume all energy is converted into electrical potential energy. Estimate the nuclear radius of the gold nucleus. Compare this value to answer A1.1 and explain what this suggests. Use your radius from A1.2 to estimate the nuclear density of gold. Assume the nucleus is spherical and contains 197 nucleons. So pause the video now and then unpause the video when you want to go through your answer. Right, in our first one, we know that the energy is equal to the electrical potential energy, so Q1 Q2 over 4 pi epsilon 0 R. We convert our MeV into joules by multiplying by 1.6 times 10 to the minus 19. We remember that the charge of an alpha is 2 times 1.6 times 10 to the minus 19, and gold we can tell is 79 times 10 times 1.6 times 10 to the minus 19. Pop in all the values and we get R to be 4.1 times 10 to the minus 14 meters. Now R is equal to R0 A to the third, where A is going to be the number of nucleons. Now we know the molar mass is 197 grams per mole, so there's 197 nucleons. We pop in the values, we get 7 times 10 to the minus 15 meters. Now the closest approach is significantly greater than the actual nuclear radius. This suggests the alpha particle does not touch the nucleus, it only gets close. Now we can work out the total mass of the nucleus by doing the total number of nucleons times by the mass of one nucleon. So we get 3.29 times 10 to the minus 25 kilograms. The volume is 4 over 3 pi r cubed, as it is a sphere. So we get 1.44 times 10 to the minus 42 meters cubed. Density is mass over volume, so it becomes 2.3 times 10 to the 17 kilograms per meter cubed. A student investigates the properties of alpha, beta and gamma radiation using a Geiger-Müller tube and a set of absorbers: paper, aluminium 2 mm thick and lead 5 mm thick. The student places each absorber between the source and the detector and records the count rate. Explain how the student can use this setup to identify each type of radiation. State one safety precaution the student should take when handling radioactive sources. A manufacturing plant uses a radioactive source to monitor the thickness of aluminium foil. The detector is placed on the opposite side of the foil from the source. The count rate is monitored continuously. Explain why a beta emitting source is suitable for this application and why alpha and gamma sources would not be appropriate. The count rate then suddenly drops significantly. The technician concludes that the foil has become too thick. Evaluate this conclusion and consider other possible explanations. So pause the video now and then unpause the video when you want to go through your answer. In our first question, we can say that alpha radiation is stopped by paper, beta radiation passes through paper but is stopped by aluminium, and gamma radiation passes through both paper and aluminium but is reduced by lead. So we would use tongs or forceps to handle the sources, would keep the source at a safe distance, or would use some shielding. Now the beta particles can penetrate aluminium foil but will be partially absorbed depending on their thickness. The alpha particles are stopped by the foil and wouldn't reach the detector. The gamma rays are too penetrating and will not show any significant change with the thickness variations of aluminium. Finally, thicker foil would absorb more particles, reducing the count rate, but other causes could include the detector being misaligned, the source having been decaying, or an increased background radiation. A student investigates how the intensity of gamma radiation varies with the distance from a point source. The student uses a Geiger-Müller tube to measure the count rate of various distances from the source. The background radiation is measured at 25 counts per minute and subtracted from all readings. The student obtains the following data. Now use the inverse square law to determine whether the data supports the relationship. The student repeats the experiment but forgets to subtract the background radiation from the new set of readings. They plot a graph of intensity against 1 over x squared and find the graph is no longer a straight line through the origin. Explain why this happens and how this affects the interpretation of the results. The student suggests that doubling the distance from the source will always reduce the intensity to 1/4. Critically evaluate this statement, considering both the theoretical and practical applications of the experiment. So in our first one, we can work out by saying k is equal to I x squared for all values, and we get 16, 16, 16.02, 16 and 16. As k is constant, our relationship is proved. Now the background radiation will add a constant to all readings, so this will cause our intensity readings to be artificially higher, especially at larger distances. Now you're going to have a greater value added at bigger distances because of the greater value of x, the area has increased in a higher amount. So the graph of I against 1 over x squared becomes non-linear and will also not pass through the origin. So this leads to an incorrect rejection of the inverse square law. Finally, doubling the distance reduces intensity to 1/4, but in practice this will assume a perfect point source and no background or scattering. Now real-world factors such as the sensitivity of the detector, background radiation and the size of the source will also cause some deviations to the values. The next question says, a research team is studying a radioactive isotope used in medical imaging. The isotope has an initial activity of 6.4 times 10 to the 5 becquerels. The activity is measured at regular intervals and found to decrease exponentially. After 18 hours, the activity is dropped to 8 times 10 to the 4 becquerels. Calculate the decay constant of the isotope. Determine the half-life of the isotope in hours. And a student claims that after two half-lives, the activity will be zero. Evaluate this statement. So, how do you answer this question? Well, in our first one, what we can say is that A is equal to A0 e to the minus lambda t. So therefore, lambda is equal to 1 over t natural log A over A0. So we pop in our values and we get 2.14 times 10 to the minus 5 seconds to the minus 1. We know that t equals log 2 over lambda, where we've just worked out lambda. Pop in the values so we get 32,400 seconds or 9 hours. Now, it's also important to know that exponential decay will never reach zero. Now, after one half-life, the activity is half the initial, so after two, it's a quarter of the initial. We could use the exponential model of A equals A0 e to the minus lambda t to show that it's exponential, so the student is incorrect. The activity will approach zero, but never reach it. A student investigates radioactive decay using popcorn as a model. The student places 200 kernels of popcorn into a microwave and records the number of unpopped kernels every 10 seconds. The student plots a curve of the number of unpopped kernels n against time t and obtains an exponential decay curve. Explain how the popcorn popping can be used as an analogy for radioactive decay. In your answer, comment on the meaning of the constant decay probability, why the decay is considered random, and why this model has limitations. The student fits an exponential model to their data, n equals n0 e to the minus lambda t. Their best fit gives a decay constant of 0.035 seconds to the minus 1. Calculate the half-life of the popcorn kernel in the microwave. After 10 seconds, the number of unpopped kernels has fallen to 150. Using the equation above and assuming n0 equals 200, calculate the decay constant lambda using the data. Comment on how this compares to the fitted value from A1.2. So pause the video now and then unpause the video when you want to go through your answer. Right, every kernel has a constant probability of popping every second. Whether a kernel pops in a given moment is random and independent of the others. The number of unpopped kernels decreases exponentially with time. Now, in reality, many kernels may differ in moisture, size, or heating, and they're not identical like atoms. T is equal to log 2 over lambda, so you pop in the values and we get 19.8 seconds. Now when we use n equals n0 e to the minus lambda t, we can rearrange it to say lambda is equal to 1 over t n over n0. Pop in our values and we get 0.0288 seconds to the minus 1. Now that is lower than the value given in A1.2. Now the fitted value may be more accurate because they have multiple data points. Early data alone can be misleading due to statistical variations in random processes. In 1909, Geiger and Marsden conducted an experiment in which alpha particles were fired at a thin gold foil. Most particles passed straight through the foil undetected, but a small number were scattered at large angles. The results contradicted the existing plum pudding model of the atom. Explain how the key observations from the scattering experiment led to a change in the accepted model of the atom. In your answer, refer to the experimental results and what they implied about the mass distribution in the atom, the charge distribution in the atom, the size of the nucleus compared to the atom. A student claims if the alpha particles are deflected, they must mean they're colliding with electrons in the atom. Evaluate this statement. Then explain how the Rutherford model of the atom changed scientific understanding of the atom and what key questions remain unanswered until the discovery of the neutron. So pause the video now and then unpause the video when you want to go through your answer. Right, most alpha particles pass through undeflected, so the atom is mostly empty space. Some alpha particles are deflected at small angles. Positive charge is not spread out. A few alpha particles are deflected greater than 90 degrees, so a positive charge is concentrated in a small dense nucleus. The mass is also concentrated in the nucleus, and the nucleus is a factor of 10 to the 4 times smaller compared to the size of the atom. Alpha particles are much more massive than electrons, so we're unlikely to be significantly deflected by them. Electrons have a negligible mass and would not cause large angle scattering. The deflection is due to the repulsion from the positively charged nuclei, not from the electrons. This led to the planetary model. The electrons are orbiting at a dense central nucleus. The improved understanding of atomic structure and stability followed, and it didn't account for the total nuclear mass. The missing mass led to the prediction of the neutron. Radiographers commonly use molecules containing fluorine-18 as traces in positron emission tomography scanning. Fluorine has a proton number of 9. Fluorine-18 decays to oxygen by beta plus decay. Write the equation for the decay of the nucleus of F18 using nuclear notation. The beta particle, the positron, produced travels only a short distance in the patient before it meets an electron and is annihilated. Calculate the wavelength of the gamma photon produced. X-rays and gamma rays are produced by different physical processes. Briefly describe both processes. F18 has a half-life of 109.7 minutes. Explain the advantage that this has for the patient, but the disadvantage that this has for the radiographers. So pause the video now, and then unpause the video when you want to go through your answer. Right, in our answer we can say that fluorine will turn to oxygen plus a beta plus particle plus our neutrino. Now we know E equals mc squared, so you get 8.2 times 10 to 14 joules. We know E equals hc over lambda, so therefore we can pop in the values. We get lambda out to be 2.4 times 10 to the minus 12 meters. Now X-rays are formed when an electron in an atom de-excites and releases a photon, while gamma rays will be more energetic, and those photons come from the decay of a nucleus in unstable isotopes. Now the advantage it has is that the half-life is short, so the exposure of the patient to the ionizing radiation is kept as low as possible, but the disadvantage is that it's only a short time to scan and diagnose the patient. Alpha particle scattering experiments led by Rutherford to propose the nuclear model of the atom took place. Alpha particles were directed towards a thin gold foil. Describe how evidence from these experiments supports the nuclear model of the atom. Pause the video now, and then unpause the video when you want to go through your answer. Right, we know in this question most particles are not deflected as they pass through the gold foil, so this indicates that there's mostly empty space inside the gold atom. Some particles were deflected from their path by small angles, so this indicates a charged centre which was deflecting alpha particles, and a very small proportion of alpha particles were deflected through more than 90 degrees, so this indicates that most of the mass of the atom is concentrated in the nucleus. In 2023, a small capsule of cesium was lost when being transported from a mine in Western Australia. The activity of the cesium in the capsule was 19 gigabecquerels, so that the decay constant for cesium-137 is about 7.3 times 10 to the minus 10 seconds to the minus 1. Calculate the mass of the cesium in the capsule. Calculate the activity of the cesium in the capsule after 2 years. Then the capsule was found after 14 days. Calculate the total energy in joules released from the capsule in 14 days. So, pause the video now, and then unpause the video when you want to go through your answer. Right, in our first one, we know lambda is equal to log 2 over the half-life. However, the half-life needs to be in seconds, so we convert our 30 years into seconds. Pop in the values, you get 7.31 times 10 to the minus 10 seconds to the minus 1. We know activity is equal to minus lambda n, so therefore n is going to therefore be equal to taking your decay constant, and so your activity divided by your decay constant. So you work that through to be 2.6 times 10 to 19. Now we then can work out the mass because we've got our activity, so therefore what we can do is multiply that therefore by the nucleon mass number I should say, so we get 5.91 times 10 to the minus 6 kilograms. Now, after this point, we can then work out the activity. So the activity is equal to A0 e to the minus lambda t. So you pop in all the values, you've got A0, which is the activity at the start. Okay, you can pop in all the values and we get 1.81 times 10 to the 10 becquerels. Finally, we know E is going to be equal to the energy that is released time per second multiplied by the number of seconds it takes in the 14 days. So what you can therefore do is work out that it's going to be 2.69 times 10 to 16 MeV. We can then convert that into joules by using our conversion factor, and we get 4.3 times 10 to 3 joules. So that brings an end to our revision session today. If we've been successful and we've learned in today's lesson, we should be able to answer A-Level Physics exam style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for AQA A-Level Physics. So this brings an end to our revision session today on paper 2 for AQA A-Level Physics on the topic of nuclear decay in the concept of nuclear physics. Thank you so much, and as always, have a lovely day. Hello and welcome to the following revision session for AQA A-Level Physics on the topic of nuclear physics, in particular looking at the concept of nuclear processes. So in today's revision session, if we've been successful and we've learned today, we should be able to answer A-Level Physics examination style questions, assess your understanding on A-Level Physics, and finally understand what topics we need to work on to improve for A-Level Physics. So how do you prepare for this revision session? When you complete your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. And in this left hand side section, write down your working out and answers to the questions in the revision session. When you're doing this, make sure to write in full sentences and show your full working out. Whilst in the right hand side, write down any bits of information which you find useful, any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you revise AQA A-Level Physics? Well, the first step is to learn the key facts. Use revision guides, class workbooks, prep notes and textbooks to learn the key ideas of the course. Then test yourself. Use Caboodle, Seneca and knowledge checkers to quickly test your own knowledge. Then practice exam style questions. Use exam preparation books, homework books, study books, workbooks to answer exam questions and to mark your own work. So the three steps are to learn the key facts, test yourself, and then practice exam style questions. So what are the key facts to do with nuclear physics? Well, the first one is mass energy equivalence. E equals mc squared, so energy and mass are interchangeable, and this applies to all forms of energy change in nuclear processes. Now, binding energy is the energy required to separate a nucleus into its constituent protons and neutrons. The mass defect is the difference between the mass of the nucleus and the sum of the individual masses of the protons and neutrons. 1U is 1.661 times 10 to the minus 27 kilograms, or 931.5 MeV. Now, the safety measures in nuclear power stations are shielding to reduce radiation exposure, remote handling of fuel rods, emergency shutdown systems to quickly stop the reaction, and the fuel is typically uranium or plutonium. Now, the radioactive waste management system is that waste is stored securely, often underground or in water pools. It must be monitored due to long half-lives and high activity. Now, the benefits of nuclear power stations are low CO2 emissions and a reliable baseload energy, but the risks include accidents and long-term waste and high storage, and then high cost. Now, induced fission is when fission is triggered by the absorption of a thermal neutron. It splits a heavy nucleus into two smaller nuclei, releasing energy, more neutrons, which may cause further fission, a chain reaction. Now, the critical mass is the minimum amount of fissile material needed to sustain a chain reaction. Now, the moderator slows down neutrons via elastic collisions to make them thermal neutrons. The material for this is either graphite or heavy water. The control rod absorbs excess neutrons to control the rate of reaction and is either boron or cadmium, whilst the coolant transfers heat from the reactor core to the turbines. Materials include water, liquid sodium and carbon dioxide. Now, you do need to understand the function of each component. Let's now have a look at some general questions to do with nuclear physics. So, what is meant by the mass defect in a nucleus? That is the difference between the mass of the separated nucleons and the mass of the bound nucleus. What is bind energy? It's the energy required to separate a nucleus into its individual protons and neutrons. What is the value of one atomic mass unit in MeV? 1U is 931.5 MeV. What does the graph of the average bind energy per nucleon against nucleon number show? It shows that nuclei with intermediate mass numbers like iron have the highest bind energy per nucleon and are therefore the most stable. Which region of the bind energy graph corresponds to nuclei likely to release energy by fission? It is the nuclei with large mass numbers. Which region of the graph indicates nuclei likely to release energy by a fusion? It is the nuclei with small mass numbers. How can bind energy calculations be used to find the energy released in a reaction? It is done by finding the difference in total bind energy before and after the reaction. What type of neutron is most effective at inducing fission in uranium-235? It is a thermal or slow-moving neutron. What is meant by a chain reaction in nuclear fission? This is a process where each fission event triggers neutrons that trigger further fission events. What is the term for the minimum amount of fissile material needed to sustain a chain reaction? It is the critical mass. What is the function of the moderator in a nuclear reactor? It is to slow down fast neutrons through elastic collisions so they can cause further fission. Which materials are commonly used as moderators? Graphite in heavy water. What is the function of control rods in a nuclear reactor? It is to absorb excess neutrons and to regulate the rate of fission reaction. Name two materials commonly used for control rods. Boron and cadmium. What is the role of the coolant in a nuclear reactor? It is to remove heat from the reactor core and transfer it to a heat exchanger or turbine system. Give one material commonly used as coolants in nuclear reactors. Either water, carbon dioxide or liquid sodium. Why are elastic collisions important in the moderation process? They allow neutrons to lose energy gradually without being absorbed, maintaining their ability to induce fission. Why must nuclear fuel be handled remotely? Because it's highly radioactive and therefore poses a health hazard to humans. What is the purpose of shielding in a nuclear power station? It's to absorb harmful radiation and protect the workers and the environment. Why is an emergency shutdown system essential in a nuclear reactor? It is to rapidly stop the chain reaction and prevent overheating or meltdown. What are some of the challenges in storing radioactive waste? It is that it remains dangerous for thousands of years and must be securely stored to avoid contamination. Let's now have a look at some questions regarding nuclear fission. The table below shows simplified nuclear data for hypothetical analysis comparing fusion and fission energy yields. Calculate the energy released per nucleon for each of the two nuclear reactions above. Which reaction releases more energy per nucleon? Show all working. Explain, using a binding energy per nucleon graph, why both fusion of light nuclei and fission of heavy nuclei release energy. You are not required to draw a graph in your answer. A nuclear policy advisor claims fission is clearly better than fusion because it releases more energy in total. Evaluate this statement using your previous calculations and further physics considerations including sustainability and practicality. So pause the video now and then unpause the video when you want to go through your answer. Right, we know that in the first question the fusion energy is going to be equal to the mass difference times by 931.5 because I'll get into MeV. So you get that to be 17.61 MeV. You divide that by the number of nucleons present, 5, so you get 3.52 MeV per nucleon. We do the same for fission and we get it out to be 0.74 MeV per nucleon. So therefore fusion releases more energy per nucleon. Now the binding energy per nucleon graph rises steeply for small a. So for fusion, light nuclei like hydrogen and helium move up the curve and release quite a lot of energy. For fission, heavy nuclei like uranium split into medium-sized nuclei which have a higher binding energy per nucleon. In both cases, the increase in binding energy per nucleon represents the energy released. Now fission will release more energy in total, but fusion is more efficient per nucleon. Now fission produces long-lived radioactive waste, but fusion does not. Fusion fuel, hydrogen isotopes, is more abundant and sustainable. However, fusion is currently technologically difficult, so practicality limits adoption. The table shows the atomic masses of selected nuclei in a fusion reactor. In a fusion reactor, a deuterium nucleus and a tritium nucleus combine to form a helium-4 nucleus and a neutron. Calculate the energy released in this fusion reaction in MeV. Explain how the graph of average binding energy per nucleon against nucleon number supports the conclusion that energy is released in this fusion reaction. A student claims that fusion always releases more energy than fission. Evaluate this claim using your understanding of nuclear binding energy and the conditions required for each process. So pause the video now and then unpause the video when you want to go through your answer. Right, in our first one, we work out the total mass before. So we add up the values of the deuterium and tritium and we get 5.030151 U. We find the total mass after by adding the helium and the neutron to get 5.011268 U. We find our mass difference by subtracting one from the other, so 0.018883 U. We then multiply by 931.5 to get into MeV, which is 17.6 MeV. Now, the binding energy per nucleon increases with fusion of like nuclei. Helium-4 has a higher binding energy per nucleon than deuterium or tritium. The increase in binding energy per nucleon means that energy is released. Now, the graph shows the fusion of like nuclei moves towards the peak of this curve. Finally, fusion of like nuclei releases large energy per nucleon due to the large increase in binding energy. The fission of heavy nuclei also releases energy, but from a different region of the curve. Now, fusion requires extreme conditions of high temperature and high pressure, so it's not always more practical or efficient than fission. The graph below shows the average binding energy per nucleon for a range of nuclei. The peak of the curve occurs near iron, with a binding energy per nucleon of approximately 8.8 MeV. A physicist proposes a hypothetical element X with a nucleon number of 60 and an average binding energy per nucleon of 7.5 MeV. Explain, using energy considerations, whether element X would be more likely to undergo fission or fusion to release energy. Justify your answer with reference to the binding energy curve. The physicists suggest that if element X could be split into two identical nuclei with a higher average binding energy per nucleon, the total mass of the products will be less than the original mass of X. Discuss this suggestion in terms of mass-energy equivalence and the implications for energy release. Evaluate the following statement. The most stable nuclei are those with the highest total binding energy. So use your understanding of nuclear stability and the binding energy per nucleon graph to support your answer. So, pause the video now, and then unpause the video when you want to go through your answer. In our first one, the binding energy per nucleon increases in fusion of light nuclei and the fission of heavy nuclei. Element X is near the middle of the curve. Now, since its binding energy per nucleon is lower than iron, increasing it would release energy. So therefore, fission is more likely if splitting increases the binding energy per nucleon. Now, if the products have a higher binding energy per nucleon, the total binding energy will increase. So this means that the mass of the products is less than the original mass. So the mass difference corresponds to the energy being released. Finally, the total binding energy increases with nucleon number, but it's not a measure of stability alone. The binding energy per nucleon is a better indicator of stability. The most stable nuclei are near the peak of the curve, with the highest binding energy per nucleon. So this statement is misleading. The higher total binding energy can mean less stability if the per nucleon value is low. The next question says, on a deep space station orbiting a gas giant, engineers are designing a power generator called the Kepler engine to sustain the outpost for 100 years. It uses nuclear reactors to generate energy, and engineers are debating whether to base the reactor on controlled fusion or microfission. To make their decision, they compare two test reactions. Calculate the energy released in each reaction using the mass data. Which reaction will produce more energy per event? Based on the binding energy per nucleon curve, explain why both reactions can release energy despite one reaction combining nuclei and the other splitting them. The Kepler engine must be maintenance-free for a century and must not produce any waste requiring human handling. Use your physics knowledge, evaluate which process, fusion or microfission, is more suitable for the station, regardless of the total energy per event. So pause the video now, then unpause the video when you want to go through your answer. Right, in our first one, the fusion mass defect is equal to the change in mass, so it's 0.00531 U. So the energy released, we multiply by 931.5 is 5.06 MeV. We then do the same for fission, and we get the energy released to be 61.48 MeV. So in this instance, fission will release more energy per event. Secondly, fission will join light nuclei to form products with a higher binding energy per nucleon. Fission splits heavy nuclei into more tightly bound fragments. Both result in a net increase in binding energy, so energy is released. Now you should pick fusion. Fission produces radioactive waste and requires waste handling systems. Fusion produces no long-lived radioactive byproducts and is better for autonomous operation. The fusion fuel is also lighter and can be potentially harvested from the gas giant that it is orbiting around. An ancient alien probe is discovered beneath the oceans of Europa. At its core is a power unit dubbed the Poseidon core, which appears to derive its energy from a chain of fusion and fission reactions. Physicists on Earth decode a fragment of its operating record. Now use the binding energy per nucleon data to determine whether the stated energy release of 7.65 MeV during the formation of carbon-12 is consistent with the physics of fusion. The second stage of the Poseidon core supposedly causes carbon-12 to split into lithium-6 and helium-6, using the binding energy per nucleon values to determine if this reaction would release or require energy. Finally, Poseidon's design appears to use an unstable isotope for controlled energy modulation, suggests a reason why the system may deliberately include a nucleus with a low binding energy per nucleon, and evaluate the risks and benefits of doing so in a self-contained, unmanned power core. So pause the video now, and then unpause the video when you want to go through your answer. In our first one, the total binding energy is 3 times by 4 helium, so it's 21.21. The total binding energy of the carbon-12 is going to be 92.16, there's 12 there, so therefore the difference in total binding energy is 70.95 MeV. So the claimed output is not consistent with this, it actually underestimates the actual energy gain found. Secondly, the total binding energy, as we just said, is going to be 92.16 for the carbon. The total binding energy of the lithium and the helium, when we work it through, is 61.26 MeV. So therefore this tells us the binding energy has decreased by 30.9 MeV. So therefore if we've lost it and it's decreased, energy is required, not released. So it's not a spontaneous reaction, we would have to trigger it. Finally, low binding nuclei are more likely to undergo decay or induce fission, so it may serve as energy control triggers. It allows clear tuning of output or emergency shutdowns via controlled instability. The risks are a potentially uncontrolled chain reaction or structural instability over time, but the benefits enable a fail-safe assembly must be weighed against the risk of radiation leakage or runaway chain reaction. The next question says, a nuclear power station uses a thermonuclear reactor to generate electricity. The reactor uses uranium-235 fuel and is designed to operate using thermal neutrons. During a routine inspection, engineers observe a slight increase in the core temperature and a higher than expected neutron flux. Explain how the moderator and control rods work together to maintain a steady rate of fission in the reactor, including your answer the physical processes involved and the importance of thermal neutrons. The engineers consider replacing the graphite moderator with a denser material to improve neutron slowing. Evaluate this decision. Then a student claims that increasing the mass of uranium fuel in the reactor will always increase the power output. Critically assess this statement considering the concept of critical mass and reactor safety. So pause the video now and then unpause the video when you want to go through your answer. Right, the moderator slows down fast neutrons via elastic collisions. Thermal neutrons are more likely to induce fission in uranium-235, so the control rods will absorb the excess neutrons to prevent a runaway chain reaction. Now, good moderators must slow the neutrons effectively without absorbing them. The denser materials may cause more inelastic collisions or could absorb neutrons. So graphite and heavy water are effective due to their low neutron absorption cross-section. So replacing graphite with a denser material could actually reduce reactor efficiency. Finally, increasing the fuel mass increases fission probability only up to the critical mass. Beyond the critical mass, the uncontrolled chain reactions may occur, so the reactor design includes control systems to manage our amount of neutrons and our neutron flux. Now, the student's claim ignores safety limits and reactor design constraints. A nuclear reactor uses uranium-235 fuel and operates using thermal neutrons. The reactor is monitored using sensors that measure neutron flux and core temperature. The table below shows data collected during a 10-minute period after a partial failure of the control rod insertion system. Describe the relationship between the neutron flux and the core temperatures shown in the data. Explain how this relates to the concept of a chain reaction in a nuclear reactor. The engineers suspect that the control rods are not functioning correctly. Use the data to evaluate this suspicion and explain the role of control rods in maintaining reactor safety. A student claims that increasing the coolant flow rate will reduce the neutron flux. Assess this claim using your understanding of the roles of the coolant and neutron moderation in the thermal reactor. So pause the video now and then unpause the video when you want to go through your answer. Right, in our first one, the neutron flux and the core temperature, as you can see from the data, both increase over time. So this is suggesting an accelerated chain reaction. More fissions release more energy, increasing the temperature. And it's a positive feedback loop if it's not controlled with control rods, as shown in the data. The control rods absorb excess neutrons to limit the chain reaction. The data shows increasing neutron flux, suggesting insufficient absorption of the neutrons. So the temperature rise supports the idea of uncontrolled fission. So the conclusion must be that the control rod failure is a plausible explanation for this. The coolant removes heat, but it doesn't directly affect how many neutrons are present. The neutron flux depends on the moderation and the control rods, not the temperature alone. Increasing the coolant flow may reduce the temperature, but not how many neutrons are present. So the student's claim is incorrect. The coolant will affect the thermal management of the reactor, not how many neutrons are present. A nuclear energy company is developing a new type of thermal nuclear reactor. They are comparing data for four materials under consideration as moderators or coolants. The aim is to maximize neutron moderation efficiency while minimizing safety risks and material degradation under reactor conditions. The table below shows the properties of four candidate materials. Using the data, explain which two materials are most suitable to act as a moderator and a coolant. Justify your choices using multiple data points from the table. Explain how the process of neutron moderation enables a sustained chain reaction to occur in a thermal reactor. A student suggests replacing heavy water with liquid sodium to save cost. Evaluate this suggestion using both physics and safety considerations. So pause the video now, and then unpause the video when you want to go through your answer. Right, the moderator should have a low atomic mass to maximise the elastic energy transfer, so this indicates that helium or graphite are the best. The moderator should have a low neutron absorption cross-section area to avoid the loss of neutrons. Helium and heavy water are the best for this. Now the coolant needs a high specific heat capacity and a high melting point. Graphite and helium score well on the melting point, and helium and heavy water have a high specific heat capacity. The liquid sodium has a high neutron absorption, so it can't be suitable as a moderator. So our final justified selection should be helium as a moderator due to the low mass and very low neutron capture, and either graphite or heavy water as the coolant. The fast neutrons that are produced in fission must be slowed down to become thermal neutrons. Moderation occurs via elastic collisions with these light nuclei. The thermal neutrons are more likely to induce fission in uranium-235, enabling that sustained chain reaction. If too many neutrons are absorbed or escaped, the mass will drop below the critical mass and the chain reaction stops. Finally, liquid sodium has a high neutron absorption, which would reduce fission rate and increase reactor instability. Sodium is highly reactive and flammable, posing greater safety risks than heavy water. Although it might be cheaper, the risk and performance trade-offs made it an unsuitable substitution. A nuclear facility generates radioactive waste from its reactors. The waste includes isotopes that vary in half-life, radiation type, and penetration depth, which affects the design of containment and disposal strategies. The table below shows data for four common waste isotopes. Using the data, identify which two isotopes pose the greatest long-term hazard to human health and the environment. Justify your answer. Explain why alpha radiation, despite being the least penetrating, requires stringent containment protocols during storage and handling. The waste facility is considering above ground storage for all four isotopes. Critically evaluate this decision using the data and your understanding of radioactive decay, including environmental and safety factors. So pause the video now, and then unpause the video when you want to go through your answer. Right, in this one, plutonium-239 has a very long half-life, so it would remain hazardous for millennia. So despite alpha radiation, if radiotoxicity if inhaled or ingested is extremely high. Now cesium-137 is also hazardous due to gamma emission and a long half-life. So therefore, the ones that have the greatest risk are going to be the plutonium-239 and the cesium-137. Secondly, alpha particles have a low penetration, but they have an extremely high ionizing power. So if inhaled or ingested, it can cause severe localized damage to tissue and DNA, possibly leading to cancer or cell death. So strict containments prevent aerosol contamination and an inhalation risk for people. Finally, above ground is suitable for short-lived isotopes such as iodine-131 as it decays quickly, but long-lived isotopes such as plutonium need secure, deep geological storage to prevent leakage. Also, gamma emitters such as cesium will require heavy shielding, which increases the infrastructure cost and the complexity of the project. Now, environmental risks could include things like natural disasters, access by terrorists, or container degradation over time, which we've got to consider. So, that brings an end to our revision session today. If we've been successful and we've learned in today's revision session, we should be able to answer A-Level Physics exam style questions, assess your understanding on A-Level Physics, and then finally understand what topics we need to improve upon for A-Level Physics. So thank you so much for watching this revision session on Paper 2 for AQA A-Level Physics, looking at the concept of nuclear physics and in particular nuclear processes. Thank you so much, and as always, have a lovely day. Hello and welcome to this revision session for AQA A-Level Physics Paper 2 on nuclear physics. So in today's revision session we're going to look at how we can answer examination questions on A-Level Physics Paper 2, in particular nuclear physics. So if we're successful we can answer A-Level Physics examination style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? When you're completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. In this section, write down your working out and answers to the questions in the revision session. When you're doing this, make sure you write your answers in full sentences and show your full working out. Whilst in the right hand side section, write down any piece of information which you find useful or any hints and tips on answering questions from this revision session. After the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising for your A-Level Physics? Well, the first step is to learn the key facts. So use the revision guides, the class workbooks, prep notes, textbooks to learn the key ideas of the course. You might want to write mind maps or write out notes yourself. The second step is to test yourself. So use things like Caboodle, Seneca and knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. The third step is to practice examination style questions. Use exam prep books, homework books, supervised study books, additional workbooks to answer exam questions and to mark your own work. Now you might wish to download your own examination past papers to do this. So your three steps are learn the key facts, then testing yourself, and then practicing exam style questions. Now in this revision session you're going to find three types of questions. The first types of questions are the general check questions. They're designed to probe your understanding of the key concepts of the topic. The second ones are the checkpoint questions. They're more challenging questions designed to place your knowledge and understanding of the topics into different contexts and applications. And then finally the assessment point questions, which are past paper exam questions which will mimic the types of questions found in public examinations. So let's have a look at some questions for nuclear physics. The first question says, in the early 20th century a series of experiments was carried out in which alpha particles were directed at thin metal foils. A simplified version of the apparatus used is shown. Describe the observations from these experiments and the conclusions that were made from these observations. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, what should you be aware about for the alpha particle scattering experiment? That most alpha particles went straight through or were undeviated, so therefore the atom is mostly empty space. A few alpha particles were deflected by small angles, so therefore very few alpha particles came straight back. So therefore that told us that there's a concentration of charge in the atom, and that's where the concentration of the mass of the atom is as well. The next question says, Rutherford's scattering experiment was done in an evacuated container. Explain why this is necessary. Then in the Rutherford's experiment, alpha particles were directed at thin gold foil. A small fraction of the alpha particles were backscattered through 180 degrees. Describe and explain how the fraction backscatter changes if the following changes are separately made. A thicker foil is used. Faster alpha particles are used. A silver foil is used. Now a silver nucleus has less positive charge but roughly the same volume as a gold nucleus. So pause the video now, then unpause the video when you want to go through your answer. Right, we needed to use an evacuated container as if there were air molecules in the container. The alpha particles would scatter off them and then distort the results, and the alpha particles could also be distorted by 6 centimeters of air. If a thicker foil was used, you get more backscattering because there's a greater chance of a closer approach to a gold nucleus, so therefore you get more than reflecting backwards. If faster alpha particles are used, fewer will get backscattered because their inertia, because they've got a higher velocity, so therefore greater inertia, will tend to carry them forwards even if they are interacting with the gold nuclei. And if a silver foil is used, fewer will get backscattered because the positive charge of the nucleus is smaller, so therefore the repulsive force between the alpha particle and the nucleus will be smaller. The next question says, before Rutherford's model, scientists believed that the atom was made from negatively charged electrons embedded in a plum pudding of positive charge that was spread throughout the atom. Explain how the alpha particle experiment proved that this old model of the atom was incorrect. Then Geiger and Marsden carried out an experiment to investigate the structure of the atom. In this experiment, alpha particles were scattered by a thin film of gold. When Rutherford analysed their results, what conclusion did he draw about the distribution of mass and charge in the atom? Then describe and explain how the experimental observations that led to these conclusions. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, the plum pudding model predicts that there'll be no large angle scattering events. An alpha particle is more massive than an electron and won't be deviated by an electron. Now, the actual experiment shows that a few alpha particles will be scattered by more than 90 degrees. Now, alpha particles must have interacted with a charged object much more massive than an electron. This object contained most of the mass of the atom, so therefore was called a nucleus. Now, in the next one, what conclusions did he draw? Well, he concluded that most of the mass was concentrated in a small space, that this space, or the nucleus, was positive and surrounded by negatively charged electrons. Now, this was shown because most alpha particles passed through undeviated through the gold, so most of the atom was empty space. Some alpha particles were deflected through large angles, showing that part of the atom is much heavier than the alpha particle and positive, and the electrons were known to exist from J.J. Thomson's experiments, so other particles in the nucleus must have been positive and heavier, and the relative number of large deflections shows the size of the nucleus. The next question says, in Rutherford's alpha scattering experiment, most of the alpha particles were not scattered. What can you conclude about the nature of the atoms? State the approximate radii of the atom and of the nucleus. In a visual model of the atom, the nucleus is represented by an apple of diameter 8 centimeters. Estimate the diameter of the atom in this model, and the figure below shows the path of an alpha particle close to the nucleus of lead. Draw arrows to represent the force on the alpha particle at A, at B, and at C. So pause the video now, then unpause the video when you want to go through your answer. Right, it shows us firstly that most of the atom is empty space because they move through undeviated. You've got to know the fact that the atom is 10 to the minus 10 meters and the nucleus is 10 to the minus 15 meters in terms of radii. So using this idea of the fact that the difference between the two of them is 10 to the 5 meters, therefore the diameter is going to be 8 centimeters times by 10 to the 5, that's the difference, so therefore it's 8,000 meters. And then this next one, you'll show that in each case the force arrows are always pointed towards the alpha particle from this, because the force on the alpha particle, and then the magnitude of the force is the largest to B, so you've got the longest arrow because they are the closest at that point. The next question says, alpha particles of kinetic energy 8.8 mega electron volts are fired at lead atoms. The charge of the nucleus and the lead is 82 E. Calculate the minimum distance the alpha particle approaches to the nucleus of the lead, the maximum electrostatic force experienced by the alpha particle, and then a tiny droplet of oil diameter 1 millimeter is placed on water. The oil spreads out as a circular disc of thickness approximately 1 atom thick. Estimate the radius of this oil disc. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can say that you can work through that the force is equal to QQ times by 4 pi epsilon 0 r squared. That is, in fact, that's the electrical force equation learned in electrical fields. Now you can see that the value is going to be of the overall, sorry, the energy, not the force. Okay, that's the gravity. That's going to be the electrostatic potential energy. My apologies. So you can work out what that energy is because it's the kinetic energy of the alpha particle. Because the alpha particle's kinetic energy goes into the electrical potential energy when it gets close to the nucleus. So you can work that by doing 8.8 times 10 to the 6, so mega electron volts into electron volts, times by 1.6 times 10 to the minus 19. So therefore, that is then electron volts into joules. That's going to be equal to the electrical potential energy, so it's 1.4 times 10 to the minus 12. That equals QQ over 4 pi epsilon 0 r squared. You make r the subject because you know what Q and Q are. Remember again that Q for the alpha particle is 2 because there's 2 protons, 2 neutrons, and then the value of charge for the nucleus is 82. It tells you there, times both by 1.6 times 10 to the minus 19. Work it all through, and D is equal to 2.68 times 10 to the minus 14 meters. Now we know the electrostatic force from the electrical fields unit is going to be equal to QQ over 4 pi epsilon 0 r as working it through. So you pop all the values in, work it all out, and then you get your answer to be 53 newtons. Now again, we can see here that the initial volume is going to be equal to the final volume, so you can work that as 4 over 3 pi r cubed is therefore equal to, again, 10 times 10 to the minus 10 pi times by r squared. Work it all through, and r is equal to 1.3 meters. The next question says, the radioactive decay of nuclei is both random and spontaneous. Explain what is meant by radioactive decay, random decay, and spontaneous decay. So pause the video now, then unpause the video and you want to go through your answer. Right, what's radioactive decay's definition? It's the emission of alpha, beta or gamma particles from an unstable nucleus trying to become more stable. Random decay indicates that it's impossible to predict which particular nucleus will decay. The rate of decay of many nuclei varies above and below the average value. And spontaneous decay means it's not affected by other nuclei or any other factors around it. So it's not affected by external conditions such as temperature. Now radioactive decay, like we said, is both random and spontaneous. The next question says, explain why you would expect beta minus particles to travel further through the air than alpha particles. Explain why you'd expect beta minus particles to travel further through the air through air than through metal. Then explain why the most strongly ionizing radiation, alpha particles, is the least penetrating, whilst the least ionizing, gamma rays, is the most penetrating. A smoke detector uses a source of alpha radiation to detect the presence of smoke in air. How does a smoke detector work, and suggest why an alpha source is more suitable for this than a beta minus or gamma source? So pause the video now, then unpause the video and you want to go through your answer. Right, so in the first one, a beta minus particle has less charge, it's smaller and it travels faster, so it's less likely to cause ionization of an atom, so therefore it'll travel further before it loses energy from this ionization process. It'll travel much further through air than through metal because air is much less dense than metal, so there's less ionization caused because there's less interactions with the atoms of the object. Now, more strongly ionized implies that the radiation will have more collisions with the particles, so therefore there's a greater loss of momentum in each collision, so therefore will not travel as far, so there'll be less penetration. Now for a smoke detector, alpha particles pass between two plates connected to electrical power supplies. The alpha particles cause ionization in the air between the plates, and therefore a small current will flow. When the smoke enters the device, the alpha particles are absorbed and there's less ionization of the air, and there's a smaller current in the external circuit. The circuit then switches on the alarm. Alpha radiation is most suitable because it's most strongly ionizing. It causes a greater current to flow, and also alpha particles are more likely to be absorbed by the smoke. Also, the range of the alpha particles is so small that it's unlikely to constitute a hazard to the user. The next question says, a radioactive source emits beta minus particles. It has an activity of 2.8 times 10 to the 7 becquerels. Estimate the number of beta minus particles emitted in a time interval of 2 minutes. State one assumption made. Then a sample of 1,000 undecayed nuclei of a nuclide whose decay constant is 0.20 seconds to the minus 1. Determine the initial activity of the sample. Estimate the activity of the sample after 1 second. So pause the video now, then unpause the video and you want to go through your answer. Right, in this first one, we know that the number of particles is equal to A, the activity, times by the change in time. So therefore it's 2.8 times 10 to the 7 times by 120 seconds, minutes into seconds, so we get 3.4 times 10 to the 9 beta particles, and that's assuming that the activity remains constant. Now, in this next one, we also know activity is equal to the negative of the decay constant times by n. So it's 0.20 times by 1,000 is equal to 200 seconds to the minus 1 or 200 becquerels. So therefore, after 1 second, 200 of those nuclei will decay, so 800 will be left. So the activity after 1 second is going to be A times by the change in time, so therefore so the decay constant times by the number, my apologies, so the decay constant 0.2, the number is now 800 because 200 have decayed from 1,000, so we get 160 or seconds to the minus 1, or 160 becquerels. The next question says, a sample of carbon-15 initially contains 500,000 undecayed nuclei. The decay constant for this isotope of carbon is 0.3 seconds to the minus 1. Determine the initial activity of the sample. A small sample of radium gives a received count rate of 20 counts per minute in a detector. It is known that the counter detects only 10% of the decays from the sample. The sample contains 1.5 times 10 to the 9 undecayed nuclei. Determine the decay constant of this form of radium. Then a radioactive sample is known to emit alpha, beta and gamma radiations. Suggest 4 reasons why the count rate measured by a Geiger counter placed next to the sample will be lower than the activity of the sample. So pause the video now, then unpause the video when you want to go through your answer. Right, again, in this first one, activity is the decay constant times by the number of nuclei. So 0.3 times by 500,000, 150,000 per second. Next one, activity is equal to 10 times by the count rate of the detector, because it's going to be 10 times by the number you got there, so it'll be 10 times by 20 per minute, so therefore it's going to be 200 per minute, so therefore in seconds it's going to be 200 divided by 60, so therefore work it all through, it's going to be approximately 10 over 3 when you work it through, so therefore decay constant is A times by N, which we looked at previously, so therefore, A over N, my apologies, so you work it all through and you get 2.2 times 10 to the minus 9 seconds to the minus 1. Now the activity is always higher than the count rate because gamma rays are not always detected because they're very weakly ionizing. The counter will always have some inefficiencies. Some radiation will be absorbed within the sample before it actually gets out and reaches the detector, and the detector is directional, so some radiation will move away from the detector rather than towards it because it won't completely surround the source. The next question says, suppose that we start an experiment with 1 times 10 to the 15 undecayed nuclei of an isotope for which the decay constant is equal to 0.02 seconds to the minus 1. Determine the number of undecayed nuclei after 20 seconds. The isotope nitrogen-13 has a half-life of 10 minutes. The sample initially contained an 8 times 10 to the 10 undecayed nuclei. Write down an equation to show how the number undecayed, n, depends on the time. Determine how many nuclei will remain after 10 minutes, then after 20 minutes. Determine how many nuclei will decay during the first 30 minutes, and then a sample of an isotope for which the decay constant is 0.10 seconds to the minus 1 contains 5 times 10 to the 9 undecayed nuclei at the start of an experiment. Determine the number of undecayed nuclei after 50 seconds and its activity after 50 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that n is equal to n0 e to the minus lambda t. So therefore, it's 1 times 10 to the 15 times by e to the power minus 0.02 times by 20 the time. So therefore, you get 6.7 times 10 to the 14 nuclei. So I get our equations n equals n0 e to the minus lambda t. So after 10 seconds, you know that half the nuclei will decay because it's got a half-life of 10 minutes. So therefore, it's 8 times 10 to the 10, half, so it's 4 times 10 to the 10. After a further 10 minutes, the next half will decay, so you've got a quarter left, so 2 times 10 to the 10. After 30 minutes, 3 half-lives have elapsed, so therefore it's halved 3 times. So therefore, what you can say is the number of original nuclei decaying will be a half, then a quarter, then an eighth. So therefore 7/8 will have decayed and an eighth will be left. So 7/8 of 3 times 10, so 8 times 10 to the 10 is 7 times 10 to the 10. The next one, you would say n equals n0 e to the minus lambda t. Pop in all the values, you get 3.4 times 10 to the 7. And then again, activity is lambda times by n. We know 0.10 is lambda. We've got n from the previous question, so we get 3.4 times 10 to the 6 becquerels. The next question says, below shows the decay of a radioactive isotope of cesium. Use the graph to determine the half-life of this nuclide in years and then find the decay constant in years to the minus 1. The decay constant of a particular isotope is known to be 3 times 10 to the minus 4 seconds to the minus 1. Determine how long it would take the activity of a sample of this substance to decrease to 1/8 of its initial value. So pause the video now and unpause the video if you want to go through your answer. Right, we can tell from the graph the half-life is the time it takes to half, so we go from 400 to 200. So therefore, that's 2.4 years. Decay constant is natural log 2 over the half-life, so therefore it's 0.29 years to the minus 1. Now you can see here how long it will take to go to 1/8 of its value. So 1/8 if its value is 3 half-lives, because one half-life to a half, second half-life to a quarter, third half-life to an eighth. So that's a very important idea. So therefore, what is 3 half-lives? Well, it's 3 times by the half-life, which we can say to be 2.4 years. So we can work it all through. So it's 6.9 times 10 to the 3 seconds. In our next question, an isotope of N decays with a half-life of 7.4 seconds. Calculate the decay constant for this nuclide. Then a sample of N contains 5,000 nuclei. Determine how many remain after a time of 14.8 seconds and then 20 seconds. Then a sample contains an isotope of half-life T to a half. Show that the fraction of the nuclei in the sample which remain undecayed after time T is given by the equation F is equal to a half to the power N, where N equals T over half-life. Calculate the fraction F after the following times: 1 half-life, 2 half-lives, 2.5 half-lives, and 8.3 half-lives. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, how do you work it through? Well, in the first one, we know that the decay constant is going to be equal, okay, to when we're working it through, it's going to be equal to log 2 over the value. So it's log 2 over 7.4, 0.94 seconds to the minus 1. Then the next one, n equals n0 e to the minus lambda t. So it's 5 times 10 to the 3 times by e to the power minus 0.094 times by 14.8 is 1250. After 20 seconds, same thing, 760. Now in the next one, we can say we can find an expression for the decay constant which we can sub into the decay equation. So the quantity F is going to be the ratio of the atoms remaining to decay to the original atoms of the sample. So we can say F equals n over n0, where T equals a half-life. So therefore F is therefore going to be equal to a half equals e to the minus lambda t over the lambda t, which T is a half-life. So take natural logs of both sides. So therefore we can say F is therefore equal to e to the power log a half times by T over the half-life. We can then work it all through. So F equals a half to T to the power, the half to the power of T over the half-life. So after 1 half-life, a half is remaining. After 2 half-lives, a quarter is remaining. After 2.5 half-lives, 0.18 are remaining. And then finally, after 8.3 half-lives, 0.032 is remaining. The next question says, the initial activity of a sample of 1 mole of radon-220 is 8.02 times 10 to the 21 seconds to the minus 1. Calculate the decay constant for this isotope and the half-life for this isotope. The figure below shows the count rate recorded when the sample of the isotope indium-116 decays. Use the graph to find the half-life of the isotope and calculate the decay constant. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that A equals a decay constant times by N. So decay constant is A over N. We've got A, we've got N, because we've got 1 mole, so it's 6 times 10 to the 23 particles in 1 mole. So it's 1.33 times 10 to the minus 2 seconds to the minus 1. Half-life is log 2, or 0.693, divided by the decay constant, which just worked out as 52 seconds. In this next question, from the graph, a half-life is the time it takes to go from 160 to 120, so that's 28 seconds. So therefore, so you can work it through, okay, to find the half-life, it's going to be 14 seconds. Now in this next one here, okay, we'll consider the decay constant is going to be the half-life times equals log 2 over the decay constant. So that's log 2 over 14, which we just worked through. So it's 4.95 times 10 to the minus 2. The next question says, the proportion of different isotopes in rocks can be used to date the rocks. The half-life of uranium-238 is 4.9 times 10 to the 9 years. A sample has 99.2% of the proportionless isotope compared with the newly formed rock. Calculate the decay constant for this isotope of uranium and calculate the age of the rock. Then the figure below shows how the randomness affects count rate. State and explain what happens if the experiment is performed using the same amount of radioactive material but at a higher temperature. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can see that the half-life is equal to log 2 over the decay constant. We've got the half-life, so we can work it through, so it's 1.4 times 10 to the minus 10 years to the minus 1. The age of the rock is going to be equal to n is equal to n is equal to n0 e to the minus lambda t. So we can rearrange that and say log n over n0 equals minus lambda t. So therefore we can work through t with all the values. Remember, 99.2% means n over n0 is 0.992. So therefore time is equal to 5.7 times 10 to the 7 years. Now in this next one, there'll be no change in count rate because radioactive decay is spontaneous, so temperature does not affect the count rate or the radioactive decay of the substance. The next question says an isotope of carbon-14 emits a beta minus particle and changes to an isotope of nitrogen. What are beta minus particles? Write a nuclear decay equation for this decay. Draw a graph with the y-axis representing the nucleon numbers between 10 and 16 and the x-axis representing the proton numbers between 4 and 10. And on the graph, mark the isotope for carbon and the daughter nucleus that this decay would produce. So pause the video now, then unpause the video when you want to go through your answer. Right, beta minus particles are fast moving electrons, and this is important for every nuclear decay that they come from the nucleus themselves. So you can see the decay equation here. Remember, the antineutrino is needed to conserve the lepton number in this decay. Then here you can see our graph here, and you can see firstly the carbon isotope. Now you can see that it turns into nitrogen. Now you can see straight away the proton number goes up by 1, turn it into nitrogen, but the overall number stays the same because, as you can tell, in the beta minus decay that a neutron turns into a proton, so the overall number of protons and neutrons, the nuclear number, stays constant. The next question says the nuclide of lead 210 decays into three separate stages by alpha and beta minus emission to another nuclide 206 Pb. So describe the structure of 210 Pb, and then alpha minus and beta minus particles. So alpha and beta minus particles are known as ionizing radiation. State and explain why such radiations can be described as ionizing. And then the two lead nuclides are shown in the graph of nucleon number A against proton number Z. Copy the graph and draw 3 arrows to represent one possible route for the 3 decays between the 2 isotopes of lead. Label each arrow to show whether it's an alpha particle or a beta minus particle emitted. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can see that the number of protons is 82 because it's the lower number, and the number of neutrons is 128 because it's 210 minus 82. Now in this next one, they are ionizing radiations because the particles are charged. So when they collide with or they pass close to other atoms, they'll knock electrons from the atoms and leave them behind those charged atoms of ions, so ionization. In this next one, you can see a possible path here. So you can see you could either have beta minus, and then you could have alpha, or you could go with alpha, beta minus, and you can see the path that it shows. Remember, one alpha decay will lose the nuclear number of 4. Okay, but then if you actually look on the value for Z, it'll go down by 2. And then whilst when you here you've got beta minus, it'll stay constant for the nuclear number, but then the Z number, the proton number, will go down by 1 each time. So the next question says, calculate the nuclear radii in femtometers of the following: helium, lithium, iron and uranium. Then how does the nuclear density for uranium compare to that of helium? And then the neutron star of mass 4 times 10 to 30 kilograms has a radius of 12 kilometers. Calculate its mean density and comment on the answer. So pause the video now, then unpause the video when you want to go through your answer. Right, the equation to work out the nuclear radius is R0 a to the power of a third. So you can do R0 as 1.2 in terms of femtometers. So therefore it's 1.2 times by 6 to the power of a third, which is the nucleon number. So it's 2.2 femtometers. The next one 2.5 femtometers. The next one 4.6 femtometers. And the next one 7.4 femtometers. Now you can work out density by doing mass over volume. So you can work out the mass by multiplying the nucleon number by 1.661 times 10 to the minus 27, which is converting the nucleon number into kilograms. Then you can divide it by the volume, which is 4 over 3 pi r cubed. So you can work out the radius of each one from the femtometers given previously. Remember, femtometers is 10 to the minus 15. So you can work it out from the previous information, and you get 2.3 times 10 to 17 for both densities. And that's an important idea, that the nuclear densities for every nucleus of every element is the same. Now in this next one, density is mass over volume. So you've got your mass there, you've got your radius of 12 kilometers, turn that into meters and do 4 over 3 pi r cubed. Work it through and you get 5.5 times 10 to 17, which is similar to the density of a nucleus. The next question says gold has a density of 19,700 kilograms per meter cubed. A mass of 193 grams of gold contains 6.02 times 10 to the 23 atoms. Use this information to estimate the volume of a gold atom and hence its radius, and state any assumptions that you make. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, we know that density is mass over volume. So 193 grams of gold occupy a volume of mass over density. So you can work that through to be equal to be 9.8 times 10 to the minus 6 meters cubed. Remember, we turned out grams into kilograms in this question. So the volume occupied by one atom is therefore the volume of 193 grams divided by the number of atoms in 193 grams. So therefore we can work it through with Avogadro. So we've got the idea of working this idea to be 1.6 times 10 to the minus 29 meters cubed. So therefore the volume of one atom is going to be 4 over 3 pi r cubed. So therefore we can rearrange that, make r the subject, and so therefore it's going to be equal to 1.6 times 10 to the minus 10 meters. And our assumption is that there's very little space between those atoms, okay, in that mass. The next question says that this question is about the nucleus of uranium-235, which has a mass of 3.89 times 10 to the minus 25 kilograms. In this information, state the number of protons and neutrons in the nucleus. The radius of a nucleus is given by the equation R equals 1.41 times 10 to the minus 15 times by a to the power of a third. Determine the density of the uranium nucleus, then explain why the total mass of the nucleons is different from the mass of a uranium nucleus, and then without calculation explain why you can determine the binding energy per nucleon for uranium-235 from its mass and the masses of a proton and a neutron. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, the number of protons is 92, it's the lower number. Number of neutrons is 143, 235 minus 92. In this next one, we can work out the volume. The volume is 4 over 3 pi r cubed. So therefore, what is our volume going to be? Well, we can work it all through and we can see that it's going to be equal to 2.76 times 10 to the minus 42 meters cubed. Therefore, we can use that to then work out what r is going to be by looking at the idea of linking in volume into when we link it into the mass as such like that. So we get 1.4 times 10 to the 17 kilograms per meter cubed. Now the mass is going to be different because when the nucleons are combined in a nucleus, they have less energy than when they're separated. Now less energy means less mass because energy has mass, so therefore the mass will be lower when they are in a nucleus. In the next one, if you sum the total mass of the separate protons and neutrons, then you subtract that from the mass of the overall uranium nuclide, you can then work out what the energy is when it goes into a nucleus by doing the energy is equal to the change in the mass between the separate protons and neutrons and the nucleus times by c squared, and this change of energy is known as the binding energy. Now the next question says approximate values for the radius of a gold atom and the radius of a gold nucleus are 10 to the minus 10 meters and 10 to the minus 15 meters respectively. Estimate the ratio of the volume of a gold atom to the volume of a gold nucleus. Then the density of gold is 19,000 kilograms per meter cubed. Estimate the density of a gold nucleus and state any assumptions that you make in your answer. So let's have a go, see if we can work it through. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know the volume of a sphere, which we assume an atom to be, and a nucleus to be 4 over 3 pi r cubed. So therefore the ratio of the volumes is 10 to the minus 10 cubed over 10 to the minus 15 cubed, which leads us to a ratio of 10 to the 15. Now the next question is 10 to the 5 cubed, which is 10 to the 15. Now in this next one, if we assume that most of the mass of the atom is contrary to the nucleus, then 19,000 kilograms of gold has a volume of 1 meter cubed. From A1, the volume of a nucleus has with this mass is 1 times 10 to the minus 15 meters cubed. So therefore, the density of gold is going to be 1.9 times 10 to the 4 divided by, of the nucleus, 1.9 times 10 to the 4, which is given in the previous information, divided by 10 to the minus 15. So therefore, it's 1.9 times 10 to the 19 kilograms per meter cubed. The next question says the sun releases vast amounts of energy. Its power output is 4 times 10 to 26 watts. Estimate how much its mass decreases each second because of this energy loss. Then calculate the energy released if a helium nucleus is formed from separate protons and neutrons. The masses are given in the table below. Calculate the energy released per nucleon. Then a golf ball has a mass of 150 grams. Calculate its increase in mass when it's travelling at 50 meters per second. What is its percentage of its rest mass? So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, E equals mc squared. So this gives us the mass decrease per second. So m equals E over c squared. We know E per second is 4 times 10 to the 26, because what's our energy per second? Divided by c squared, 3 times 10 to the 8 squared. So it's 4.4 times 10 to the 9 kilograms. We know helium nuclei are formed from 2 protons and 2 neutrons. The energy release is the difference in mass between the 4 separate nucleons and the helium nucleus. So if you work out this difference in the masses, it's going to be 5.04 times 10 to the minus 29 kilograms. E equals mc squared. So pop that into the E equals mc squared equations, and our energy is 4.5 times 10 to the minus 12 joules. So what's the energy release per nucleon? Well, there's 4 of them, and there's 4.5 times 10 to the 12 over 4 of them, so therefore it's 1.1 times 10 to the minus 12 joules. In this next question, the kinetic energy of a golf ball is a half mv squared, so it's a half times by the mass in kilograms, 0.150, times by 50 squared is 187.5 joules. The mass energy equivalent of the ball is going to be equal to m equals E over c squared, so it's 187.5 over c squared, 2.1 times 10 to the minus 15 kilograms. So find the difference as a percentage of its rest mass, which is 0.150 kilograms. So it's 1.4 times 10 to the minus 12%, which is about right for an object on the real world scale. The next question says the mass of an atom of iron is 55.934937 U. Calculate its mass in kilograms. Then the mass of an atom of oxygen is 2.656015 times 10 to the minus 26 kilograms. Calculate its mass in U. The table below gives the mass in U of several nuclides. Determine the mass excess of helium, and then one nuclide has a negative mass excess. Name the nuclide and determine its mass excess. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, how can you convert from U into kilograms? Multiply by 1.661 times 10 to the minus 27, so it's 9.2880 times 10 to the minus 26 kilograms. We can reverse it by dividing by 1.661 times 10 to the minus 27, so it's 15.995 U. In this next one, the mass excess is the mass of the helium nucleus minus the mass of the 4 separate nuclei, so it's 0.002602. The mass excess of potassium is a negative, so therefore it's 0.036002. The next question says a nucleus of beryllium decays into an isotope of boron by beta minus emission. The chemical symbol for boron is B. Write a nuclear decay equation for the nucleus of beryllium-10 and then calculate the energy released in this decay and state its form. So pause the video now, then unpause the video when you want to go through your answer. Right, the nuclear decay equation is beryllium will go into boron, and you'll have an electron because you notice the proton numbers are going up by 1, the nuclear numbers stay constant, so the only thing that can conserve those numbers is an electron. The next one, the mass difference, is the difference in mass between the beryllium at the start and then the boron and the electron. So you can find the difference to be 9.89044 times 10 to the minus 31 kilograms. So therefore the energy release is E equals mc squared. So you get 8.9 times 10 to the minus 14 joules. And this tends to be released as the kinetic energy of the products in this particular decay. The next question says, in a nuclear reactor, the mass of uranium and the fission fragments fall to a rate of 70 micrograms per second. Calculate the maximum power output from the reactor, assuming it's 100% efficient. The equation below shows the radioactive decay of radon-222. Calculate the total energy output from this decay and state what forms of energy are produced. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know E equals mc squared, so 70 times 10 to the minus 6 times by 3 times 10 to the 8, so every second you've got an energy being released of 6.3 times 10 to the 9 joules. The energy per second is the power, so that is the answer, so it's 6.3 gigawatts. In the next one, we know the mass deficit is going to be equal to the mass of the radon minus the mass of the plutonium, the alpha particle, and the gamma, but obviously there's no mass for the gamma. So you can work that through, and you get your difference to be 0.005 U. We can convert that into kilograms by multiplying by 1.661 times 10 to the minus 27. So it's 8.3 times 10 to the minus 30 kilograms. Energy released E equals mc squared. Pop it through, and you get 7.47 times 10 to the minus 13 joules, and that'll be be as kinetic energy of the alpha particle, and because you've got a gamma ray, some of the energy will go as the gamma ray as well. The next question says, calculate the binding energy per nucleon for the nuclide iron. And then the mass of beryllium nucleus is 1.33 times 10 to the minus 26 kilograms. A proton and a neutron have a mass of about 1.67 times 10 to the minus 27 kilograms. For the nucleus of beryllium, determine the mass defect in kilograms, the binding energy, and the binding energy per nucleon. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, the mass of the neutrons is going to be 56 minus 23, so it's 30 for the iron. So find the mass defect by doing the mass of the protons and the mass of the neutrons, and then subtract it from the overall mass of the nucleus. So you get 8.680 times 10 to the minus 28 kilograms. Binding energy is E equals mc squared. Pop all the values in, and you get 7.812 times 10 to the minus 11 joules. We can then divide it by the total number of nucleons, the large number on the symbol, so 56, so it's 14 times 10 to the minus 13 joules. In the next question, the mass defect is going to be the number of protons and the number of neutrons in beryllium, which is 4 and 4, minus the mass of the beryllium, so it's 6 times 10 to the minus 29 kilograms. The binding energy, so you multiply that by c squared, so you get 5.4 times 10 to the minus 12. You can divide that by 1.6 times 10 to the minus 19 to get into EV, so it's 3.4 times 10 to the 7 EV. So the binding energy per nucleon is then that value divided by the number of nucleons, which is 56, which is going to be 8. So therefore it's 6.8 times 10 to the minus 13 joules, or 4.2 times 10 to the 6 EV. The next question says, explain why hydrogen does not appear on the graph below, and then using the binding energy graph below, suggest why fission is unlikely to occur with light nuclei and why fusion is unlikely to occur for heavier nuclei. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can see that hydrogen is a single nucleon, so therefore it can't have a binding energy, because the binding energy is the energy lost by the nucleons as they go into a nucleus. And then the second one, fission for lighter nuclei is unlikely because the products of the fission have a smaller binding energy per nucleon, so be less stable, and then the reaction therefore would require an input of external energy, and then for fusion it's unlikely for the same reason as well. The next question says, a carbon-12 atom consists of 6 protons, 6 neutrons, 6 electrons. The unified atomic mass unit U is defined as 1/12 of the mass of a carbon-12 atom. Calculate the mass defect in kilograms, the binding energy, and the binding energy per nucleon. So pause the video now, then unpause the video when you want to go through your answer. Right, so the mass defect is going to be the mass of the individual components minus the mass of the nucleus, so you get 0.098934 U. Multiply that by 1.661 times 10 to the minus 27 to get it in kilograms to be 1.64 times 10 to the minus 28 kilograms. Multiply that by c squared to get the binding energy, so it's 1.48 times 10 to the minus 11 joules. Divide that then by the number of nucleons, which is 12, because you've got 6 protons and 6 neutrons. Electrons are nucleons. So you get 1.23 times 10 to the minus 12 joules. The next question says, the fusion reaction which holds the most promise for the generation is the fusion of tritium and deuterium. The equation below shows the process. So calculate the change in mass in this reaction, the energy released in this reaction, and the energy released if 1 mole of deuterium reacted with 1 mole of tritium. So pause the video now, then unpause the video when you want to go through your answers. Right, the change in mass is going to be equal to the mass of the things at the start, so it'll be tritium and deuterium, minus the mass of the helium and the mass of the hydrogen after the end. So we get our difference to be 0.020271 U. Multiply that by 1.661 times 10 to the minus 27 to get into kilograms to be 3.365 times 10 to the minus 29 kilograms. Multiply by c squared to get the energy release, so it's 3.028 times 10 to the minus 12 joules. And then if we want, that's the energy released per atoms, the energy released per mole, with that multiplied by Avogadro's constant, the number of molecules in 1 mole. So we multiply that by Avogadro and we get 1.823 times 10 to 12 joules. The next question says, a student supervised by their teacher carries out an experiment with 3 unlabeled radioactive sources. The student is told that each source emits only one type of radiation. One emits gamma, one emits beta minus, one emits beta plus particles. The student has the following equipment: a selection of materials of different thicknesses, a strong magnet, and a radiation counter. Explain how the student can use this equipment to determine safely which radiation each source emits. So pause the video now, then unpause the video when you want to go through your answer. Right, so what method would you use? So you'd measure the background count and subtract from your source count, very important in any radioactive experiment. You'd clamp the source pointing away from you. You'd have safety precautions, so like handle the source with tongs, limit the time of exposure. You'd record the count over a fixed period and then investigate how the count rate varies with the range. You could place aluminium sheets between the source and radiation counter. You could then set up magnetic fields at right angles to emission direction to investigate if they deflect as charged particles, or you can move the radiation counter to find the direction of the deflection. Now you should note that gamma has the longest range in air. Beta minus and beta plus have a similar range. Gamma will penetrate aluminium, which is a few millimeters thick, but beta will not. Gamma is undeflected by a magnet because it's neutral, but beta radiation is deflected by a magnet because they are charged. Beta plus and beta minus, as they're oppositely charged, will deflect in opposite directions in a magnetic field. And then you can use Fleming's left-hand law to actually determine the charge on whether it is a positron, the beta plus, or the electron, the beta minus particle. And then also remember as well, with beta plus, the current is in the same direction as the motion because it's a positively charged particle, so you can see it as if it was conventional current. The next question says, in beta plus decay, a proton decays into 3 other particles. Write the nuclear equation for this process, and then a student supervised by a teacher carries an experiment with the 3 unlabeled radioactive sources as indicated before. So, explain how you can use this equipment safely to determine the radiation emission. So in this first one, it is going to be a proton will go to a neutron, and then you're also going to have your neutrino will be present as well, okay, and also your positron will work also. Now the next question says the student gathers the following data and plots the following graph of data. The half thickness value X for a particular shielded material and type of radiation is often used in industry, and the value of the thickness of the shielding required to reduce the incident of the radiation by half. The student thinks that the relationship shown by the data of the corrected count versus the shielding is exponential. Use the information provided and describe and perform a mathematical test to support this conclusion. Calculate the half thickness, describing also the method you would ensure a reliable value. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one, how could you use the data? So the data from the table could be used to find the constant reduction factor between the successive points. So you should do multiple data points and find that you've got a constant value. Or you could do a natural log value for each count rate, and then the difference between the successive values is calculated and found to be constant. So that's how you can determine exponentiality, either with using natural logs or from taking the values and finding the rate of change, and the rate of change should be constant. In terms of using the graph, the count rate decreases with increase in thickness. The relationship does show exponential decrease of count rate, and then because it shows the count rate halves at regular intervals with that of shielding. The thickness for the count rate should be dropped by the same fraction as it changes each amount of time, and the gradient of the curve at different thicknesses shows it halves at roughly regular values. You should find from the graph that the half thickness is at about 2 centimeters. You can use the graph to take measurements of values of half thickness. You should take multiple measurements to take an average value, so you can work it all through with your precision to be about 2.1 centimeters. The next question says, the cesium is a radioactive isotope produced during the fission of uranium. State what is meant by fission, then cesium decays by emitting beta radiation. Complete the nuclear decay for cesium. Explain why the emission of an antineutrino in the decay leads to a range of energies for the beta minus particle. Cesium is a major source of radiation from radioactive waste. A nuclear fission reactor produces about 24 kilograms of cesium each year. A website states that 24 kilograms of cesium has the same activity as 2,000 kilograms of radium. Assess whether this statement is correct, and then cesium may enter plants grown in a contaminated area. The radiation from 100 grams of plant material grown in a contaminated area can have a count rate as high as 500 becquerels. As a count rate of 150 per minute is considered safe, determine the time taken for the count rate from 25 grams of plant material grown in a contaminated to fall to a safe level. So pause the video now, then unpause the video when you want to go through your answer. Right, so what is meant by fission? That is when a massive nucleus splits into 2 or more smaller fragments of roughly equal mass, and you'll also produce some neutrons as well. Now in this particular equation, you can see that the cesium is 13555, the barium's gone up by 1 proton, so it's 56. You then got your beta minus is 0 minus 1, and your antineutrino is 0 0. It has no charge, so that all the values are conserved. Why do you get a decay? Well, because momentum is therefore conserved. The energy released is shared between the beta minus and the antineutrino, and therefore it's shared between a multiple number of particles in the decay, so it varies it out. In this next one, we know that the number of particles is 24 over 136.9 times by 1.66 times 10 to the minus 27. That's the mass of one particle. So therefore, it's 1.0 times 10.06 times 10 to the 26 particles. We know that the decay constant is log 2 over the activity, which is therefore going to be, so the half-life, my apologies, which is 30.2 times by 3.15 times 10 to the 7, because we work in seconds, not years. So it's 7.29 times 10 to the minus 10 seconds to the minus 1. So activity is lambda n. So therefore we've got lambda, we've got n, multiply the two together, and we get 7.73 times 10 to the 16 becquerels, which is not equal to 7.3 times 10 to the 16 becquerels, so it's not correct. In the next question, we know A is equal to a quarter of the initial, because if we look down, we can see how long it's taken to drop there. So time taken to drop is going to be, it's quartered, so therefore it's going to be a quarter of the initial, so 125 becquerels. So therefore, in terms of in seconds, that's therefore going to be 2.5 in your activity, because you know it's 150 count rate per minute, so therefore per second is 2.5 becquerels. So therefore we can do A equals A0 e to the power minus lambda t, pop in all the values, we can then use that to work out what lambda is, and therefore t is going to be, so t is going to be 5.37 times 10 to the 9 seconds. The next question says, radon is a radioactive gas and emits alpha particles. Explain what is meant by the activity of a radioactive source and give its unit. The half-life of radon is 3.3 times 10 to the 5 seconds. Determine the time it takes for a sample of radon to decay to 20% of its initial activity, and then discuss the extent to which alpha particles are a risk to the human body. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, the definition of activity is the rate of decay, or the number of decays per second of the nucleus, and it's measured in becquerels. We know for the next one that the decay constant is log 2 over the half-life. So we've got the half-life in seconds, so we've got the decay constant to be 2.1 times 10 to the minus 6 seconds to the minus 1. We can say that A equals A0 e to the minus t minus lambda t, so therefore e to the lambda t is A over A0, so you can work out what t is to therefore be 7.7 times 10 to the 5 seconds, or 8.9 days. Now, alpha particles are safe outside the body because they're stopped by skin. They're only dangerous if inhaled or swallowed, but they are highly ionizing, so if they are swallowed, they can damage DNA, kill cells, cause cancer, and cause radiation poisoning. The next question says, potassium-40 is a radioactive isotope and can decay by beta minus emission. Complete the nuclear decay, so the equation for the decay of potassium by beta minus emission, and then occasionally potassium decays by emitting a beta plus particle. Give two similarities between the beta minus and the beta plus particle. A fertilizer contains potassium chloride. The activity of a sample of the fertilizer used to radioactive potassium is 48.6 becquerels. It's claimed that the time t for the activity of a sample to fall below the background count rate will be more than 9 times 10 to the 9 years. To deduce whether this claim is correct. The background count is 0.42 becquerels, and the half-life of potassium is 1.25 times 10 to the 9 years. So pause the video now, then unpause the video when you want to go through your answer. Right, we should know that if in this next one we know that calcium has 20, and by beta minus emission it's gained a proton, so potassium must be 19, but the overall nuclear number stays the same, so calcium has 40, and we also know that beta minus particle is always 0 minus 1. Now we know that beta minus and beta plus are particles and antiparticles, they'll have the same mass, they're both leptons, they're both fundamental particles, they'll have the same magnitude of charge, they'll both be deflected in electrical magnetic fields, and they'll both have the same ionizing power. Now in this next one, we know the decay constant is log 2 over the half-life, so the decay constant is 5.55 times 10 to the minus 9 years to the minus 1. We can then work out what time is going to be by saying A equals A0 e to the minus lambda t, rearrange that, make t the subject, and we get 8.56 times 10 to the 9 years. The next question says that cesium-137 is a common product of uranium fission. Very small samples of cesium can be used to calibrate radiation detector equipment. Cesium decays to an isotope of barium by emitting a beta minus particle. Complete the nuclear equation for the decay of cesium. Then a sample of pure cesium has an activity of 7,400 becquerels. Calculate the mass in kilograms of the sample. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one again, we know that by this decay, that cesium has lost a proton, so therefore it's going to be 55, the same number of nucleons, 137, beta minus, 0 minus 1, and again it's the same process going through here, except now we're looking for mass, so how we could work it through is do decay constants log 2 over the half-life, so we work out the half-life in seconds, so 7.29 times 10 to the minus 10 seconds to the minus 1. We know that n is going to be equal to the activity over the decay, over the half-life, so therefore you can work it, sorry, not the half-life, the decay constant, so therefore it's going to be 7,400 over the decay constant is 1.02 times 10 to 13. Then we can work out what the mass is, because we know the mass is going to be the number of particles times by the number of nucleons that we have, multiplied by 1.661 times 10 to the minus 27 kilograms, so it's 2.31 times 10 to the minus 12 kilograms. The next question says, a nucleus of thorium-230 is unstable and decays to a nucleus of radium-226 by emitting an alpha particle. The table shows the masses of the particles involved. Determine the energy in joules released when a nucleus of thorium-230 emits an alpha particle. Then determine the time taken in years for 90% of the thorium in the sample to decay to radium. The half-life of thorium is 75,400 years. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can say, right, E equals mc squared. Now, mass is going to be the difference in the mass between the thorium and the radium. Okay, and also you can see that the alpha particle is also produced. So therefore, it's 5.1 times 10 to the minus 3u. Multiply that by the conversion factor to turn that into kilograms, 8.47 times 10 to the minus 30. So E equals mc squared. So 7.62 times 10 to the minus 13 joules. We know that the decay constant is log 2 over the half-life. So we can see that's 9.19 times 10 to the minus 6 years to the minus 1. We can then say A equals A0 e to the minus lambda t, but we can go A over A0 and equals e to the minus lambda t. Now, because it's lost 90% of it, therefore what's left is 10%, so therefore A over A0 is 0.1. Pop in all the values, we get out t to be 2.51 times 10 to 5 years. In the next question, in 1935, Irene and Frédéric Joliot-Curie were awarded a Nobel Prize for the discovery of artificial radioactivity. They bombarded an aluminium sheet with alpha particles to produce a radioactive isotope of phosphorus as in the nuclear equation below. Identify particle X, calculate the energy released in joules of this nuclear reaction, and then radioactive phosphorus was one of the first artificially produced isotopes to be used in the diagnosis of cancerous tumours. The isotope of potassium is injected into the body and collects in the tumour. Radiation is detected outside the person's body. It is a positron emitter with a half-life of almost 15 days. Explain why it's suitable for this procedure. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can see that X is going to be a neutron. Because it's got a nucleon number of 1, but a proton number of 0, it must be a neutron. In this next one, we work out the change in mass between the particles before and the particles afterwards. So the change in mass given in the units is 5 times 10 to the minus 4 gigaelectron volts per c squared. So therefore the energy, E equals mc squared, so therefore the c squared cancels through. The energy is 5 times 10 to the minus 4 gigaelectron volts. We can then turn that into joules by multiplying it by 10 to the 9 to get into electron volts, then by 1.6 times 10 to the minus 19 to get into joules, so it's 8 times 10 to the minus 14 joules. In this next one, positrons will annihilate with electrons in the body to produce gamma radiation. Now, gamma radiation from annihilation can penetrate out the body. Now, the half-life is long enough to allow the procedure to perform, but not too long to not give a large radiation dose to the person. The next question says, radium-226 decays into radon. Assume that 98% of the energy released in this process is converted to the kinetic energy of the alpha particle. Use the data below to determine the speed of the alpha particle. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, we can work out the change in mass by doing the mass before and the two masses afterwards and find the difference. So therefore we find it to be 0.005229 U. We convert this into mega electron volts by using a bit of a cheat, multiplying by 931.5. We can then convert this into then joules by multiplying by 1.6 times 10 to the minus 13, because it's mega electron volts. So therefore it's 7.8 times 10 to the minus 13 joules. So V therefore is going to be, well, E equals a half mv squared. So therefore V is equal to the square root of 2 times by 0.98 E, because it's 98% of the energy. So divided by the mass, so therefore it's 1.52 times 10 to the 7 meters per second. The next question says the bismuth isotope decays by alpha decay to an isotope of thallium. Fill in the missing numbers for this decay. Then determine whether or not a kinetic energy of 3.6 mega electron volts, the alpha particle in the above reaction, is consistent with the data below. The half-life of bismuth is 1.9 times 10 to the 19 years. Calculate the activity of 1 gram of bismuth. Then determine the number of nuclei in 1 gram of bismuth which will decay in 5 years. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one we know that alpha is going to be 42 on the right hand side, therefore thallium to balance must be 205 on the top and 81 on the bottom. In this next one, what's the values going to be? Well, you find the masses of 83 protons and 126 neutrons for bismuth to be 210.7021 U. So therefore the binding energy, we can then work it through by then finding the difference. So therefore you get 164.83. Then subtract the mass defect for the bismuth mass. So therefore you can find the difference and you get 0.0039 U. Multiply that by 231.5 to get 3.63 mega electron volts. Then this next one, how do you work it through? Well, the half-life is log 2 over the decay constant, so pop in the values and you get 1.16 times 10 to the minus 27. The mass of one atom we know is going to be 209 times by the conversion factor into kilograms, so 1.6 times 10 to the minus 27. The number of nuclei is therefore going to be 2.88 times 10 to 21, so therefore our answer is going to be 3.3 times 10 to the minus 6 becquerels, and therefore we can work out how many decay in 5 years by using the values working through to be 525. In the next question, in the cover main sequence star, nuclear fusion is converting hydrogen into helium. Explain the conditions required to bring about and maintain fusion in a main sequence star. A helium nucleus is a particularly stable nucleus containing 2 protons and 2 neutrons. Calculate the binding energy per nucleon in joules of a helium nucleus. Then the binding energy per nucleon of a helium is relatively large. Explain why this makes the helium nucleus particularly stable. So pause the video now, then unpause the video when you want to go through your answer. Right, fusion happens when there's a high enough temperature in the core, because this gives the protons a large enough kinetic energy, so the protons can get large enough to fuse because there's an electrostatic repulsion between the nuclei because they've got the same charge. You also need a very high density to maintain a high collision rate to maintain this fusion process, and that also leads to high temperature. In the next one, find the mass difference before and afterwards. So you find the mass difference before and afterwards to be 28.1 mega electron volts per c squared. So when we say E equals mc squared, the c squared cancels through, so the binding energy is 28.1 MeV. So therefore we can turn that into electron volts by times by 10 to the 6, then times into joules by times by 1.6 times 10 to the minus 19. So it's 4.496 times 10 to the minus 12 joules. So divided by the number of nucleons that are in the helium, 4. So it's 1.124 times 10 to the minus 12 joules. Now the large binding energy per nucleon means that the energy required to remove the one nucleon from the nucleus is very large, so therefore it's very large to break apart it's very large energies are needed to break apart this helium nucleus, so therefore it's very stable. Now the decay products have a lower binding energy per nucleon, which means that it's less stable because you need less energy to separate it apart. The next question says, a nucleus of polonium-210 decays to lead-206 by emitting an alpha particle. The masses are shown in the table. Show that the energy released in the decay is about 9 times 10 to the minus 13 joules. 98% of the energy from the decay is released as kinetic energy of an alpha particle. Calculate the velocity of the alpha particle immediately after the decay, and explain why all the energy from the decay is released as kinetic energy of the alpha particle. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, What's the difference in mass? So you find the mass before, the mass afterwards, and it's 9.63 times 10 to the minus 30 kilograms is the difference. E equals mc squared. Pop it through, 8.67 times 10 to the minus 1 joules. The next one, when you work it out, what happens through? So you'll take this value and you'll times by 0.98. That is therefore equal to the kinetic energy of the alpha particle, which is a half mv squared. You know the mass of the alpha particle from the information given, so you can say that therefore that equals a half mv squared. You can say v therefore is equal to the square root of 2 times by this energy over the mass, so it's 1.60 times 10 to the 7 meters per second. Now, why does not all of it get released as kinetic energy? Well, momentum must be conserved in this decay, so if the alpha particle has a movement, well, the lead nucleus must recoil to also counteract that, obviously in much slower speed because it's a much higher mass, so therefore it must take up some of the energy, of the kinetic energy of the reaction in that process. The next question says, alpha particle scattering led Rutherford to propose the nuclear model of the atom. Alpha particles were directed towards a thin gold foil. Describe how evidence from these experiments supports the nuclear model of the atom. So pause the video now, then unpause the video when you want to go through your answer. Right, it tells us that most of the particles are not deflected because they pass straight through the gold foil, which indicates that most of the gold atom is empty space. Some particles were deflected from their path by small angles. This indicates that there's a charge center to the atom with the same charge as the alpha particles. Then a small proportion were deflected through 90 degrees, they were backscattered, so most of the mass must be concentrated in this small point, which we call the nucleus. The next question says, radiographers commonly use molecules containing fluorine as tracers in positron emission tomography scanning. Fluorine has a proton number of 9 and decays into oxygen by beta plus decay. Write the equation for the decay of a nucleus of fluorine using nuclear notation. The beta plus particle produced travels only a short distance in the patient before it meets an electron and is annihilated. Calculate the wavelength of the gamma photons produced. Then X-rays and gamma rays are produced by different physical processes. Briefly describe both processes, and then fluorine has a half-life of 109.7 minutes. Explain the advantage that this has for the patient, but the disadvantage it has for the radiographers. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, the fluorine turns into the oxygen, and you've got your beta plus particle, and you've got your neutrino there to conserve lepton number. We know the nucleon number and the proton number are conserved before and afterwards. In this next one, E equals mc squared. So you've got the mass of the particle. It is the same as the mass of an electron because it's the antiparticle. So it's 8.2 times 10 to the minus 14 joules. E equals hc over lambda. So we know that from de Broglie and from and then you work it through to say, well, E equals hc over lambda, pop it all through and you get the value there, and then lambda therefore is 3 times 10 to the 8 over 1.2367 times 10 to the 20, so it's 2.42 times 10 to the minus 12 meters. Now, X-rays are formed when electrons de-excite and then release via gamma emission, whilst gamma rays come from the decay of the nuclei in the atom itself. Now, the advantage of having this half-life is that the half-life is short, so the exposure to the patient for ionizing radiation is kept low as possible, but the disadvantage is for the radiographers, they have a very short time to diagnose the patient from the information. The next question says, in 2023, a small capsule of cesium was lost from being transported from a mine in Western Australia. The activity of the cesium in the capsule was 19 gigabecquerels. Show that the decay constant for cesium is about 7.3 times 10 to the minus 10 seconds to the minus 1. Calculate the mass of the cesium in this capsule. Calculate the activity of the cesium in the capsule after 2 years. The capsule was found after 14 days. Calculate the total energy in joules released from the capsule in 14 days. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that the decay constant is log 2 over the half-life. Pop it all through. Half-life needs to be in seconds though, so therefore it's 7.31 times 10 to the minus 10 seconds to the minus 1. The mass we know well. Activity is equal to minus decay constant times by n. We know that for that n is therefore going to be the activity, which we know is to be 19 gigabecquerels, which is 19 times 10 to the 9, over the number of particles, over the decay constant, which is 7.31 times 10 to the minus 10, which is 2.60 times 10 to the 19. So therefore the mass is therefore going to be the number of molecules which you have times by 1.661 times 10 to the minus 27, because that turns into kilograms, so therefore it's 5.91 times 10 to the minus 6 kilograms. The activity after 2 years, well, we use the decay equation of A equals A0 e to the minus lambda t. We know the initial activity is 19 gigabecquerels, or 19 times 10 to the 9. We know what the decay constant is, and we know the time. Remember, after this, it has to be in seconds though, not years. So we work it through to be 1.81 times 10 to the 10 becquerels. And then this last one, we know that the energy is going to be equal to the activity multiplied by the time in seconds. So it'll be 14 times 86,400, because we're turning our days into seconds. Then we multiply by the energy released in 1 decay, which is 1.17 mega electron volts. So we get 6.96 times 10 to the 16 MeV. We can then convert that into joules by multiplying by 1.61 times 10 to the minus 19 times, get the mega up by times by 10 to the 6. So you get 4.30 times 10 to the 3 joules. The next question says, radium is a radioactive element. The most common isotope of radium has a half-life of almost 2,000 years. A sample of radium can remain at higher temperature than a surrounding for a long period of time. Explain how a sample of radium is able to release significant amounts of energy over a long period of time. So pause the video now, and then unpause the video when you want to go through your answer. Right, in this one, the rate of decay depends upon the number of unstable nuclei in the sample, because A equals minus decay constant times by N. Radium has a large half-life, so the unstable nuclei present are there for a long time. So when a nucleus decays, there's going to be a small decrease in the mass, and therefore when that happens, energy is released from the binding energy equation, E equals mc squared. Now, because the change in mass is small, C, 3 times 10 to the 8 squared, is still large, so a significant amount of energy is released. This energy released becomes the kinetic energy of the atoms in the sample, so therefore that links into the temperature of the sample, so the temperature is much higher of the sample compared to the surroundings. The next question says, in the early part of the 20th century, Rutherford made the first observation of an element being changed into a different element. Alpha particles were fired at nitrogen atoms. The nuclear equation for this reaction is shown. Calculate the minimum energy in MeV required for this reaction to take place, then calculate the minimum energy in MeV for this reaction to take place. So pause the video now, then unpause the video when you want to go through your answer. Right, so we know that the change in mass will be given by doing the mass of the products of this reactants before, subtracted the products of the decay afterwards. So we get 2.07 times 10 to the minus 30 kilograms from the information given. We know that the binding energy is mc squared, so we can then multiply that by c squared, so it's 1.863 times by 10 to the minus 13 joules. We can therefore say we can convert that into EV by dividing by 1.6 times 10 to the minus 19. So therefore it's 1.16 times 10 to the 6 EV, or 1.16 mega electron volts. Now, therefore we know that the momentum and energy must be conserved in a decay. So the products must have the kinetic energy after the reaction. So therefore it must be the same as it was before. So therefore you can work it through that way as well. So that brings an end to our revision session today. If we're being successful and we've learned in this revision session, we should be able to answer A-Level Physics examination style questions for nuclear physics, assess our understanding on A-Level Physics on the nuclear physics module, then understand what topics we need to improve upon for nuclear physics. So thank you so much for attending this revision session on nuclear physics for AQA A-Level Physics Paper 2. Thank you so much and have a lovely day. Hello and welcome to this revision session on nuclear physics. So in today's revision session we're going to look at how we can answer examination questions for AQA A-Level nuclear physics. So if we've been successful and we've learned in today's lesson, we should be able to answer A-Level physics examination style questions. We should be able to assess your own understanding on A-Level physics, and then finally understand what topics you need to improve upon for A-Level physics. So how should you carry out this revision session? Well, when completing your work in this revision session, divide your piece of paper into 2 sections. Make the section on the left hand side larger than that on the right hand side. On the left hand section, write down your working out answers to the questions in the revision session, and when you do this, make sure you write your answers in full sentences and show your full working out. Now on the right hand side, write down any pieces of information which you find useful, or any hints and tips on answering questions from this revision session. At the end of this revision session, write up these notes into a revision sheet for you to use use independently. So how should you be revising for A-level physics? So the first step is learn the key facts. Use your revision guides, your class workbooks, your student prep notes, your textbooks to learn the key ideas of the course. So you may wish to make mind maps or to write out notes yourself. The second step is to test yourself. So use the Caboodle learning platform, use the Seneca learning platform, use your own knowledge checker to quickly test your own knowledge, and you might want to do this with your own cue cards. Step 3 is then to practice exam style questions. So use the exam prep books, homework books, supervised study books, additional workbooks to help answer exam questions and mark your own work, and you may wish to download your own exam past papers to do this. So these 3 steps of learn the key facts, then testing yourself, and then practicing exam style questions are how you can effectively revise A-level physics. So let's have a go at a few multiple choice questions first. So uranium-238 decays by emitting alpha particles. It's not possible to influence when the decay of a particular nucleus of uranium-238 will occur. This is because radioactive decay is what? So pause the video now, then unpause the video when you want to go through your answer. Right, our answer is B. That's because the ability not to influence the rate of decay is known as spontaneous. So from the other ones, involving high energy is irrelevant, occurring very quickly is irrelevant, and occurring randomly means you can't dictate or detail which of the radii is, or nuclei, is going to decay, only that a certain number is. Second question, which of the following is not a source of background radiation? So pause the video now, then unpause the video when you want to go through your answer. Well, the answer is C, because microwaves are non-ionizing radiation, so don't contribute to the background radiation, which is in the background ionizing radiation of the Earth. Question 3. Americium is a radioisotope that decays by emitting alpha particles. The difference in mass in MeV over c squared between an americium nucleus and the products of the decay is delta M. The energy release in the decay is given by which equation? So pause the video now, then unpause the video when you want to go through your answer. Right, the answer is A, because if we say delta E is equal to delta MC squared, well, we can say that delta E is equal to delta M times by MEV over C squared times by C squared. We know that because the difference in mass we've just been told is given by the units MEV over C squared. So those C squareds cancel through, which tells us our energy release is delta M MEV. Question 4. A deuterium is an isotope of hydrogen. A nucleus of deuterium has a mass of Md. It contains one proton of mass Mp and one neutron of mass Mn. Which of the following can be used to calculate the binding energy of a deuterium nucleus? So pause the video now, then unpause the video when you want to go through your answer. Right, the answer is C, because binding energy is the change in mass over c squared, because you know that delta E is equal to m raised to mc squared, so you can work it through like that. So it's the mass of our nucleons minus the mass of the nucleus, that's our change in mass, over c squared. So when we work it through, we get our value of C, which is times c squared, not divide, sorry, times by c squared. Question 5. The graph shows how the binding energy per nucleon varies with the nucleon number for a stable nuclei. What is the approximate total binding energy for 184W? So pause the video now, then unpause the video when you want to go through your answer. Right, so the answer is D. Why is that? Well, the y-axis of our graph tells us it's the binding energy per nucleon. So what you would do is you go to 184 on your x-axis and go up and find out the value of the average binding energy per nucleon, which we see is 8. Then you go to multiply by 184, which will give us our value of 1472 MeV. That is our binding energy in MeV. Then to convert that into joules, you multiply by 1.6 times 10 to the minus 13. That gives us our answer of 2.36 times 10 to the minus 10 joules, which we want to work in picojoules, which is going to be, as you can work out, 10 to the minus 9 is then going to be 236 picojoules. So our answer is going to be D. Let's now have a look at a few longer questions on nuclear physics. So the first question is, nuclear radii can be estimated using the closest approach of an alpha particle. Nuclear radii can be determined using electron diffraction. Discuss the benefits of using electron diffraction rather than the closest approach of an alpha particle to evaluate nuclear radii. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? So it's the idea that what's our issue with using the distance of closest approach? Well, the major one is the distance depends on the alpha particle's kinetic energy, because the kinetic energy of the alpha particle turns into electrical potential energy due to repulsion between the alpha particle and the nucleus. So the alpha approach is a calculation, okay, that you're just working it out by taking your measurements, but the idea that the electron diffraction, okay, is actually a measurement you're actually working out. Now the alpha particle distance of closest approach is the maximum possible distance that it can get at before it repels. So therefore it puts an upper limit on the nuclear radius, but it doesn't actually measure that nuclear radius, because it also includes the distance between the actual alpha particle when it repels and the nucleus, as well as the nuclear radius. So our electron diffraction method actually measures the nuclear radius, while the distance of closest approach is an estimation, which is an upper limit, because it also includes an extra bit of space. The next question says that show that the relationship between the nuclear radius r and the nuclear number a is given by the following equation, where ρ is the density of the nuclear material. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this particular question? Well, the first thing you've got to do is think about how you can use your different equations to bring them all together. So the first thing to note is that the total mass of the nucleus is going to be A, which is the nuclear number, times by U, the atomic mass unit. We know our equation for the volume of a sphere is 4 over 3 pi r cubed, and we know that density is mass over volume. So we can pop in our equation for mass, AU, divided by our equation for volume, 4 over 3 pi r cubed, and then we can rearrange it to make big R the subject. So we can make that through and we get our answer as follows. Let's have a look at the next question. State what is meant by the binding energy of a nucleus, and then a possible fission of uranium-235 is represented by the following equation, and then calculate in joules the energy released in this equation. So pause the video now, then unpause the video when you want to go through your answer. Right, the first one's a very interesting one because it's just a definition you've got to learn. So the binding energy is the work that must be done to separate the nucleus into all of its separate nucleons, its neutrons and protons. Remember, even though it's called binding energy, it's the energy to separate all the nucleons. Or you can think of it as the energy released when a nucleus is formed from its constituent neutrons and protons. Now this next question, how can you work out the energy released in this reaction? So what you've got to do is as follows. You look at your particular your particular process, and you know you've got a uranium and you've got a neutron. Now a neutron actually has, you'll note, it doesn't on the table because it doesn't have any binding energy because it's just one neutron. But afterwards you've got cesium and rubidium. So what you want to do is work out the binding energy of uranium by multiplying the value in the table by 235, because that's the binding energy per nucleon and you need the total binding energy. You'll then find the same for cesium by multiplying it by 136 and rubidium by times it by 97. Then you can find out the binding energy difference between the uranium at the start and the cesium and rubidium afterwards, and then to convert that into that's our value in MeV. Then to convert that into joules, how can we work that through then? Well, you can times by 1.6 times 10 to the minus 13 to get our answer of 2.71 times 10 to the minus 10 joules. Next question. The average energy released by the fission of a uranium-235 nucleus in a reactor core is 3.2 times 10 to the minus 11 joules. The fission of uranium-235 generates a power of 1.5 gigawatts in the core. Calculate the average mass of uranium-235 that undergoes fission in 1 second in the reactor core. So pause the video now, then unpause the video when you want to go through this answer. Right, so how do you answer this particular question? Well, you've got to understand that you want to be working out the energy produced, okay, by one particular nucleus. So you can divide the power or energy per reaction. Then what you can do is convert the number of nuclei you've got into a mass. Now you can do that because you know that your molar mass is 235 grams. So at that point you can then work out what's going on in that aspect. So you can say it's 1.83 times 10 to the minus 5 kilograms per second. Now again, please do remember that power is the energy per second. So it's 1 1.5 gigajoules per second. So you can say that in 1 second that the total energy is 1.5 gigajoules. The energy released by one fission is 3.2 times 10 to the minus 11 joules. So you can work out how many fission events take place, and then you can work it through like that. Next question. The thermal neutrons in the core can be modelled as particles of an ideal gas. The effective temperature of this gas is 850 Kelvin. Calculate the root mean square for the thermal neutrons for this model. So pause this video now, then unpause this video when you want to go through this answer. Right, and so whilst this question is in nuclear physics and it's on the topic of fission, it's actually part of the ideal gas topic in thermal physics. So what you've got to do is, if you are given the temperature in Kelvin, you can use our following equation of a half mv squared, or half root mean squared, velocity root mean squared equals 3 over 2 kt. Why 3 over 2 kt? Because you're given the value of t and you know k is a constant. Now you know what the mass of the neutron is going to be because you can find it on the back, in the back of the equation book, and then we can equate them together and work out what CRMS squared is. You then square root it to get CRMS, so we get 4.6 times 10 to the 3 meters per second. Next question. Explain the role of the control rods in ensuring a constant power output in a nuclear reactor core. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to be able to explain how a control rod works and produces a consistent power output or a consistent fission rate in a nuclear reactor core. So the idea is that the control rod absorbs neutrons, and the depth or length at which the control rod is in the reactor vessel affects how many neutrons are absorbed, so therefore affects your fission rate. So you've got to understand that if you want a constant power output or a constant fission rate, you need 1 neutron per fission event going on to induce another fission. So the idea is that the control rod absorbs any more above 1, so it tends to either be 2 or 3 in a fission event, so the control rod will absorb them. So then you can say that because you've got a constant rate of fission, you've then got a constant power output in your nuclear reactor. The next question says that the mass of a nucleus of californium-252 is 252.03 U. Calculate the mass defect of the nucleus of californium-252. So pause the video now, then unpause the video when you want to go through your answer. Right, how do you calculate this? So the first thing you've got to notice is that you've got, in californium, you've got 98 protons and you've got 154 neutrons, because it's 252 minus 98. So that's the first mark you would get. The second mark is then trying to calculate the mass of 98 protons and 154 neutrons in U. Now again, the value of the proton and neutron in U is given in the equation book in the exam. So therefore you can work out the total, which is 254.04862 U. You can then subtract the mass of the nucleus to therefore be 252.03, so then you get the difference between the two of them, and then finally, because you're trying to work it in kilograms, you've got to convert from U into kilograms, okay, which you can work through again because the conversion factor is in the back of the equation book, so you can then use them that way, and you get your answer to be 3.3 or 3.4 times 10 to the minus 27 kilograms. The next question says the spontaneous fission of californium-252 produces a xenon nucleus, a ruthenium nucleus and 4 neutrons. Calculate in MeV the amount of energy released in this particular fission process. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you calculate the energy released in the process? Well, the first thing you've got to do is you've got to work out the difference in mass in this particular process. So the first thing you'll notice is that they don't give you the mass of the neutron, but you've got to always consider it. So please remember that this is given in the back of the equation book, and then you can use that in your calculation. So you've got your mass in U for californium, then you would work out the mass of the xenon plus the mass of the ruthenium plus the mass of the 4 neutrons, and at that point you can then find the mass difference by subtracting the mass of the xenon, ruthenium and the 4 neutrons added all together from the mass of the californium. That then gives you a value in U of your mass difference but before and after. Then you convert that into MeV by multiplying by 931.3, which is our shortcut to get our answer from mass difference into energy release in MeV, which is 210 MeV. Next question. Some proposed fusion reactors will use a fuel of deuterium and tritium. The fusion reaction produces helium-4 and a neutron. Firstly, explain why this reaction will only occur when the fuel is at a very high temperature. Then the temperature of the fuel in one reactor is 1.2 gigakelvin. Calculate the average kinetic energy of a deuterium nucleus in the fuel, assuming the fuel behaves as an ideal gas. So pause the video now, then unpause the video when you want to go through your answer. Right, the first one is you've got to understand the conditions of the fusion process and why we have that. Well, it's the idea that the nuclei need to come within a few femtometers to fuse. Because at that range, the strong attractive force is then the dominant interaction, so it will pull the nuclei together to fuse them together. But they need to have a high kinetic energy, which is linked to a high temperature, because temperature is linked in direct proportion to kinetic energy, to overcome the positive repulsion of our two nuclei. Now the second question is asking the average kinetic energy of a deuterium nucleus in the fuel, assuming it behaves like an ideal gas. So what we can then do is we can say that the average kinetic energy is equal to a half mc RMS squared, which is our average kinetic energy value, equals 3 over 2 kT. So we can just say it equals 3 over 2 kT because it's an ideal gas. K is the Boltzmann constant, which is given in the equation book, and K is going to be 1.2 times 10 to the 9, because we've got to get rid of the giga there to then work out our value, and we get 2.5 times 10 to the minus 14 joules. Right, the next question says an estimate of the closest approach between the deuterium nucleus and the tritium nucleus can be made using answers. Explain how this estimation can be made. Right, so pause the video now, then unpause the video when you want to go through your answer. Right, so how can you do this? Well, how can you work out the distance of closest approach from an estimation? So what you've got to do is you've got to understand you've got your kinetic energy before, and this kinetic energy transfers into electrical potential energy when you have the distance of closest approach going on. So we can say that a half mv squared is going to be equal to q1 q2 over 4 pi epsilon 0 r. You can then rearrange this equation, make r the subject, and either have your kinetic energy as the Ke term or as a half mv squared, pop the values in and work it through. Our next question says table 2 shows the binding energy per nucleon for two nuclides involved in the fusion reaction. The energy released in this fusion reaction is 17.589 MeV. So calculate in joules the binding energy of the tritium nuclide. So pause the video now, then unpause the video when you want to go through your answer. So how would you answer this particular question? So what you've got to do is you've got to work out the two binding energies. So the idea, okay, that in this fusion process you're going to have that two hydrogens are fusing into one helium. So what you will therefore do is you'll have your two hydrogens, you add them up, you then have your helium and then add that up, then you calculate the differences to find the binding energy per, work it through, and then convert that into joules from your MeV by times by 1.6 times 10 to the minus 19. It's also worth noting that the table shows us the binding energy per nucleon. So when we need to work out the total binding energy, remember to multiply the values in the table by the nucleon number. So for hydrogen you'd multiply it by 2, and for helium you'd multiply it by 4, because the helium has 4 nucleons and the hydrogen has 2. The next question says that alpha particle comes to rest at a distance of 5.5 times 10 to the minus 14 meters from the center of a gold nucleus. Calculate the speed of the alpha particle when it's at a large distance from the nucleus, ignoring relativistic effects. So pause the video now, then unpause the video when you want to go through your answer. Again, where does this come from? It's the idea that our kinetic energy has turned into electrical potential energy. So what we can therefore do is we can therefore link the two together. So the loss of kinetic energy is equal to the gain in potential energy. So we can say a half mv squared is equal to q1 q2 over 4 pi epsilon 0 r, and then we could rearrange this all and make v the subject. Now what's very important when you do this is you recognize what Q1 and Q2 are. Now Q1 is the charge of the alpha particle, so it's 2 times by 1.6 times 10 to the minus 19, whilst Q2 is the charge of the gold nucleus, which is going to be 79 because that's the number of protons, so you can see from the question, times by 1.6 times 10 to the minus 19 coulombs. And then you can work it through like that, and you get an answer of about 1.4 times 10 to the 7 meters per second. The next question says the nuclear radius of the gold nucleus is 6.98 times 10 to the minus 15 meters. Calculate the nuclear radius of silver. Then all nuclei have this approximately the same density. State one conclusion about the nucleons in a nucleus that can be deduced from this fact. So pause the video now, then unpause the video when you want to go through your answers. Right, so the first one, you've got to use our nuclear radius equation, and that is R is equal to R0 a to the power of a third. So what you need to be doing is as follows. You can either ratio the two, or I will prefer it, is you can use the information in the top line for gold to work out our value of R0, our constant. So you can say that 6.98 times 10 to the minus 15 equals R0 times by 79 to the power of a third. You can then use that to work out R0, and because R0 is a constant, you can then substitute that into our value for the silver. So you can therefore say the radius of silver is the value of R0 you've just worked out multiplied by the value of A, which is going to be 107 to the power of a third. Sorry, in the one before I should have said that the value of A is 197, not 79, because A is the number of nucleons, so it's the number of protons and neutrons. My apologies for that. So to work out our value nuclear radius for silver, it's R0, which we just calculated previously, times by 107 to the power of a third, which is 5.7 times 10 to the minus 15 meters. Now, what conclusion can you come up with the fact that all nuclei have the same density? Well, it's that the nucleons are incompressible. You can't push them in any further, or that the nucleons have a consistent separation in all nuclei, or that the idea that neutrons and protons have a similar mass and a similar volume, because as a result they can't get any closer or further apart from each other. The next question says, a thermal nuclear reactor uses enriched uranium as its fuel. This is a fuel in which the ratio of uranium-235 to uranium-238 has been artificially increased from that found in this naturally occurring ore. Describe what happens when the neutrons interact with uranium-235 and uranium-238 nuclei in a thermal nuclear reactor. So pause the video now, then unpause the video when you want to go through your answer. Well, it's very important that you know what happens when a neutron hits both of these values. So the first one is when a neutron is going to interact with the uranium-235, it will absorb the uranium-235 will absorb the neutron. It then becomes uranium-236. It will then carry out nuclear fission and then give out more neutrons. Now, when uranium-238 absorbs a neutron, it doesn't carry out fission immediately. So what will happen is it will actually gain a neutron, or it will scatter the neutron, and the uranium could become uranium-239. Then actually what happens is beta decay occurs and it becomes plutonium, and then that carries out fission later. We're just looking at what it does when it's uranium. The next question says the amounts of uranium-238 and 235 in the ore decrease due to radioactive decay at different rates. A sample of uranium ore today contains 993 grams of uranium-238. The mass of uranium-238 in the sample was greater 2 times 10 to the 9 years ago. Firstly, show that the mass of uranium-238 in the sample at this time was about 1.4 kilograms, and that a thermal nuclear reactor requires a minimum of 3% of its uranium mass to be uranium-235. The ratio of uranium-235 to uranium-238 in the ore has changed over time. 2 times 10 to the 9 years ago, the sample had contained 52 grams of uranium-235, so deduce whether the sample had high enough uranium-235 to be used in a reactor 2 times 10 to the 9 years ago. So pause the video now, then unpause the video when you want to go through your answer. Right, so what's the first thing you've got to do? Well, in this first question, you've got to use the idea of nuclear decay. Now, the equation comes from n equals n0 e to the power minus lambda t. So what you can then do is say nt, the value of n is for the present day, and n0 is for the value being in the past. So we can therefore say that the mass of uranium is going to be 1.36 times by 0.993. So that's how much uranium-238 we've got, which is 1.35 kilograms. Now we can then work out a half-life as well. So we could also say that we could also do it by saying the half-life is 4.5 times 10 to the 9 years. So how many half-lives are taking place? Well, it's going to be 0.44. So therefore we can say that 2 to the power of 4 over 9, or 0.44, is 1.36. So therefore we do 1.36 times by 0.993, because that's how much there is. It's 1.35 kilograms. Now for the second question, you can just ratio them. So you do your ratio of the number of 235 divided by number of 238 plus 235, and you get 3.6 to 3.7%. So therefore it can carry out nuclear fission because it's above 3%. The next question says, a thermal nuclear reactor uses a moderator to lower the kinetic energy of fast-moving neutrons. Explain why the kinetic energy of neutrons must be reduced in a thermal nuclear reactor. Then, as a result of the collision with an atom of a particular moderator, a neutron loses 63% of its kinetic energy. A neutron has an initial kinetic energy of 2 MeV. Calculate the kinetic energy of the neutron after 5 collisions. So pause the video now, then unpause the video when you want to go through your answers. So in this first one, explain why with the kinetic energy the neutrons must be reduced in a thermal nuclear reactor. Well, they've got to be travelling slower to increase the probability of fission, because it will allow the neutron to be absorbed by the uranium-235, because there need to be thermal neutrons or slow moving neutrons for them to be absorbed by the nucleus. Now the second question is actually using a bit of mathematics. It's working out that it goes down by 63% each time. Now what you can do is you can say that the final energy is going to be 1 minus 0.63 times by the incident, or 0.37 of the incident. So you can work it out each time, and you can say if it's going down by 5 times, it's going to be 0.37 to the power of 5 times by E0, because that's just a bit of mathematics working it through. I mean, you could work out 63% of the value each time for 5 particular times, or you could just do 0.37, which is 1 minus 0.63, a loss of 63%. So because it's gone down to 37%, so you do 0.37 to the power of 5 times by our starting value, which is 1.4 times 10 to the 4 eV. The next question says, one fission process which can occur in a thermal nuclear reactor is represented by this equation. Calculating MeV, the energy released in this fission process. So pause the video now, then unpause the video when you want to go through the answer. Right, so what do you do here? So you work out your mass before and you work out your mass afterwards, and don't forget your neutrons. So you work out what the mass before was, then subtract it from the mass afterwards, or vice versa, and then you find out there's a mass difference of 0.180 U. Now it's then important to note, by the way, when you're doing this particular question, because you want to work out the energy release in MeV, if you've got a mass difference in U, you multiply by 931.3 or 931.5, either is fine, to get your value in MeV. It's a quick shortcut, which is 168 MeV. The next question says, many magazines and newspaper articles focus on the risks of nuclear power. State 3 benefits of using nuclear power. So pause the video now, then unpause the video when you want to go through your answer. Well, you've got to be aware of both the advantages and disadvantages of using nuclear power. So what's our advantages? Advantage number 1, there's small amounts of fossil fuels used, not no fossil fuels used. You've got to be very careful about that, because you're still going to use fossil fuels in transport and in some ways in the power station itself. So little greenhouse gas, or there's little global warming, or there's less CO2, or there's less climate change. It's very important to say that you use less fossil fuels, so there's less greenhouse gases produced, not that there's none. Secondly, because you're using less fossil fuels, the air is going to be cleaner. Thirdly, you're using small amounts of the uranium as your fuel source to get a large amount of power or energy, so the uranium has a very high energy per kilogram. Nuclear power can be produced continuously and can be very constant, while some renewables, for example, can be dependent on the conditions that you require, but nuclear is a very consistent and reliable power source. You can also have nuclear power can adjust the power output quickly by changing the depth of the control rod. And then finally, we can also produce medical isotopes in our reactor, which can be used for our benefit. Now, you can also mention the fact that nuclear fuel can be obtained from very stable countries at the minute, as opposed to oil or gas. It also can help produce nuclear weapons, because you're producing those isotopes, which is useful. And also it's the idea there's less transportation required, so there's less fossil fuels produced that way, because you don't need to transfer as much fuel from power station to power station. So I hope you've enjoyed this particular revision session. So if we've been successful in this revision session, we'll be able to answer A-level physics examination style questions, assess our understanding on A-level physics, and understand what topics we need to improve upon for A-level physics. So I hope you've enjoyed this revision session on nuclear physics for AQA A-Level Physics. Thank you very much for watching and have a lovely day.